There's a point between Earth and the Sun where gravity balances perfectly, and that's where we put telescopes to watch the cosmos. Between Earth and the Sun, there's a spot called Lagrange point 1, or L1. At this location, the gravitational pull of Earth and the Sun cancel out in a way that allows objects to stay in a stable position relative to both. This makes it ideal for placing satellites and telescopes. The main advantage is that it allows continuous observation of the Sun or space beyond Earth without interruption. L1 is located about 1.5 million kilometers from Earth in the direction of the Sun. Objects placed there orbit the Sun in sync with Earth, effectively staying parked between the two. Because they're not pulled too strongly toward either body, they can maintain position with minimal fuel use. This location is highly useful for solar monitoring and deep space observation. The SOHO spacecraft, Solar and Heliospheric Observatory, is stationed at L1. It monitors the Sun 24/7, helping to predict solar flares and coronal mass ejections that might affect Earth. Another mission, DSCOVR, also sits at L1, watching for changes in space weather and Earth's energy balance. These missions benefit from the uninterrupted view that L1 provides. L1 is just one of 5 Lagrange points in the Earth-Sun system. These are regions where combined gravitational and orbital forces allow small objects to stay relatively fixed with respect to two larger bodies. L2, another key location, is on the opposite side of Earth, away from the Sun, ideal for space telescopes. The James Webb Space Telescope, JWST, is located near L2, not L1, so it can always face deep space without looking at the Sun. Meanwhile, L1 remains the go-to spot for solar observation. Each point has different advantages depending on the mission's goal. Satellites at L1 are not truly stationary, but require small orbital adjustments to stay on track. Most orbit around L1 in a pattern called a halo orbit. This helps them avoid drifting away while keeping a clear view of the Sun or Earth depending on the spacecraft's role. The balance at L1 isn't due to equal gravitational force alone, it's also due to the centrifugal force from the satellite's orbital motion. The combined effect creates a point where a spacecraft can remain with relatively low energy input. That makes L1 a fuel-efficient location for long-term missions. L1 is also important for early warnings. Satellites there can detect solar storms before the particles reach Earth. This gives space agencies and power companies 15 to 60 minutes of advance notice, which helps protect satellites, astronauts, and electrical systems on Earth. The concept of Lagrange points was first proposed by Joseph Louis Lagrange in the 18th century. These gravitational balancing points exist in all two-body systems, including Earth-Moon and Sun-Jupiter. They're now central to space mission planning and orbital mechanics. So when we want to spy on the cosmos or keep an eye on the Sun, we often park telescopes and satellites at gravitational sweet spots like L1 and L2. These locations let us watch space continuously, with minimal fuel and maximum stability. A day on Venus is longer than its entire year. Venus has an extremely slow rotation. It takes about 243 Earth days to complete one full spin on its axis, but it only takes about 225 Earth days to orbit the Sun once. This means a day on Venus is longer than a year there, a unique situation in the solar system. To make it more confusing, Venus rotates in the opposite direction to most other planets, a movement called retrograde rotation. If you stood on Venus, ignoring the hostile conditions, the Sun would appear to rise in the west and set in the east. This reverse rotation adds to the length of its solar day. A solar day, the time from one sunrise to the next on Venus, is about 117 Earth days. That's shorter than its sidereal day because of how Venus moves around the Sun while rotating. But still, the planet spins so slowly that its surface barely turns over the course of a day. This unusual rotation has major consequences for Venus's climate. The planet doesn't have the strong Coriolis forces that affect weather patterns on Earth. As a result, Venus has a very slow atmospheric circulation near the surface, though its upper atmosphere moves much faster. Despite its slow spin, Venus has incredibly high surface temperatures, over 460 degrees Celsius, hotter than Mercury. That's because of a runaway greenhouse effect trapping heat. The long days and thick clouds also prevent efficient heat loss at night, leading to nearly uniform temperatures across the planet. Venus's rotation is so slow that early astronomers thought the planet might not rotate at all. It wasn't until the 20th century, using radar from Earth and spacecraft like Magellan, that scientists measured its rotation speed accurately. It surprised everyone by being so slow and retrograde. Tidal interactions between Venus and the Sun may have contributed to this odd spin. Some models suggest Venus used to rotate faster, but solar tides gradually slowed and reversed its motion. The exact process is still debated, but it likely involved internal and external forces over billions of years. Venus's extreme day length and retrograde spin make it a challenge for robotic missions. Landers must withstand long exposure to heat and survive without sunlight for extended periods. That's one reason why most missions have focused on flybys and atmospheric study rather than surface exploration. Understanding Venus's rotation helps scientists learn more about planetary dynamics and evolution. It shows how orbital and rotational changes can shape a planet's environment dramatically. It also helps explain why Venus, though Earth-like in size, turned out so different. In summary, Venus spins so slowly and backward that its day lasts longer than its year. This affects everything from climate to mission planning, making it one of the most unusual and extreme planets in our solar system. Saturn could float in water. It's less dense than it. Saturn is the least dense planet in the solar system. Its average density is about 0.687 grams per cubic centimeter, which is less than the density of water, 1.0 grams per cubic centimeter. In theory, if you had a large enough bathtub, say the size of a planet, Saturn would float in it. Of course, such a bathtub doesn't exist, and Saturn is mostly made of hydrogen and helium, both very light elements. Its massive volume spreads out this low-mass material, creating an average density that's extremely low for a planet of its size. This makes it unique among the gas giants. Saturn is about 95 times more massive than Earth, but its huge size results in low density. Its atmosphere is made of light gases, and while it may have a small rocky or icy core, the core is only a small percentage of the total mass. The rest is mostly gas, compressed under gravity. Despite its low density, Saturn's gravitational pull is still strong because of its large mass. On Saturn, you would weigh slightly more than on Earth, but you couldn't stand on anything solid. There's no surface, just thick layers of gas and clouds transitioning to denser materials deeper down. Its low density contributes to its fast rotation and shape. Saturn spins rapidly, completing a full rotation in just over 10.5 hours. This speed causes it to bulge at the equator and flatten at the poles, making it the most visibly oblate planet in the solar system. Saturn's rings, made of ice and rock, do not contribute much to its mass, but they do enhance its striking appearance and help it stand out in density comparisons. Even with the rings, the planet is still light enough to float, at least in theory. The concept of a floating planet is often used as a fun fact, but it's based on real physical properties. Scientists use density to understand a planet's internal structure, composition, and formation history. Saturn's low density tells us it formed far from the Sun, in a cold region rich in light gases. The other gas giants, Jupiter, Uranus, and Neptune, are denser than Saturn. Jupiter is denser because of stronger gravity compressing its material. Uranus and Neptune are richer in ices and heavier compounds, raising their average density compared to Saturn. Saturn's density is a reminder that not all large planets are heavy in the traditional sense. Size and mass are related, but not the same. A planet can be big and light if it's made mostly of low-density material. In summary, Saturn is the only planet that would float in water thanks to its extremely low average density. It's a giant ball of mostly hydrogen and helium, making it huge but light for its volume, and a standout in our solar system. Jupiter has colossal storms that last for centuries, like the iconic Great Red Spot. Jupiter's atmosphere is home to giant, long-lasting storms, the most famous being the Great Red Spot. This is a massive anticyclonic storm, a system where winds rotate in the opposite direction of a cyclone, located in Jupiter's southern hemisphere. It's so large that 2 to 3 Earths could fit inside it. It's been continuously observed since at least the 1600s. The Great Red Spot has wind speeds of over 400 kilometers per hour, and its persistence is unlike anything seen on Earth. On our planet, storms are broken up by land, oceans, and changing temperatures, but Jupiter has no solid surface and enormous internal heat, which helps fuel and sustain these storms for very long periods. The storm sits between two powerful jet streams that trap it in place, preventing it from drifting. This contributes to its stability and longevity. While it has shrunk in recent decades, it remains active, and scientists are not sure if it will fade completely or change form. Beneath the cloud tops, the storm likely extends deep into Jupiter's atmosphere. The Juno spacecraft measured gravity anomalies in the region, suggesting the Great Red Spot may go down hundreds of kilometers. This would make it much deeper than any weather system on Earth. Jupiter's atmosphere is made of hydrogen, helium, ammonia, and other compounds, and it has strong internal heat. This energy drives powerful convection, creating bands, jet streams, and vortices. Some of these storms merge or split, but the largest ones can persist for years or centuries. The colors of the Great Red Spot are still a mystery. The red hue might come from chemicals like phosphorus or sulfur, altered by UV radiation from the sun. Different chemical reactions at different altitudes create the distinct multi-layered appearance. There are also other giant storms on Jupiter, such as oval-shaped white and brown spots. Some of them form when smaller storms collide and merge, creating new, long-lived systems. These storms provide scientists with insight into fluid dynamics on a massive scale. Jupiter's rapid rotation, about 10 hours per day, also helps shape its atmosphere. It creates strong Coriolis effects, which stretch storms into rotating systems. Combined with internal heat, this leads to extremely dynamic and stable weather patterns. Studying these storms helps scientists understand how atmospheres work on gas giants. It also informs models used for exoplanet research, since many exoplanets are similar in size and composition to Jupiter. The planet serves as a natural laboratory for extreme atmospheric physics. One of Saturn's moons, Hyperion, spins in a completely chaotic way and looks like a natural spacecraft. Hyperion is one of Saturn's many moons, but it stands out due to its strange shape and unpredictable rotation. It's about 270 kilometers across and looks like a giant irregular sponge. Its low density, strange motion, and odd surface make it one of the most unusual bodies in the solar system. Hyperion is not spherical, it's heavily cratered and elongated, giving it a look that's often compared to a sponge or spacecraft. Its shape is due to its low gravity and lack of geological activity. It hasn't rounded out like most other large moons. Its rotation is completely chaotic, meaning it doesn't spin in a steady or predictable way. Instead, its axis of rotation tumbles randomly as it orbits Saturn. This happens because it's irregularly shaped and interacts gravitationally with nearby Titan, Saturn's largest moon. Hyperion's tumbling motion means there's no consistent day or night. Sunlight hits different parts unpredictably. Space missions like Cassini confirmed this behavior by tracking how the moon spun differently on each pass. No other moon of this size shows rotation this unstable. Its density is very low, only about 0.55 grams per cubic centimeter, lower than water. This means it's likely made mostly of ice with a lot of empty space, which also explains its porous surface. The surface doesn't compress easily, so when meteoroids hit it, they create deep, sharp-edged craters. These craters give Hyperion its sponge-like look. Because the surface is so porous, impacts don't spread shock waves efficiently, so craters stay narrow and steep. The overall result is a very jagged and pitted body, unlike smoother moons like Enceladus or Europa. Hyperion is also slightly electrically charged. The Cassini mission detected signs that particles from Saturn's magnetic field interact with its surface, giving it a mild electrostatic environment. This interaction could affect dust motion or surface chemistry. Its orbit is eccentric and tilted, which adds to its chaotic behavior. Combined with its gravitational interactions and irregular shape, this keeps the rotation unstable over long periods. It's one of the few moons known to stay in a non-synchronous, tumbling state. Hyperion doesn't have an atmosphere, liquid water, or signs of life, but it's still of scientific interest because it helps us understand how irregular shapes and gravitational forces affect rotation and surface development. It's a good test case for complex orbital dynamics. Pluto may have underground liquid oceans, even so far from the Sun. Despite being extremely far from the Sun, Pluto may still hold liquid water beneath its icy crust. This idea is supported by data from the New Horizons mission, which revealed surface features that suggest geological activity. For a world this cold and small, the idea of subsurface oceans was once considered unlikely. Pluto's surface temperature is about -230 degrees Celsius, cold enough to freeze almost everything solid. Yet features like cracks, ridges, and resurfaced plains suggest movement below the surface. This movement could be caused by an internal ocean pushing against the crust. A key area of interest is Sputnik Planitia, a massive icy basin. It appears to be sinking into Pluto's interior, which could only happen if there's a dense liquid layer beneath it. Otherwise, the crust wouldn't behave the way it does. This supports the idea of a subsurface ocean. Some models suggest that radioactive decay in Pluto's rocky core provides enough heat to keep water in a liquid state, insulated by thick layers of ice. This internal heat source might be weak, but it's enough, combined with insulation, to prevent complete freezing. The ocean, if it exists, would be trapped under dozens or even hundreds of kilometers of ice. It may contain salts, ammonia, or other antifreeze-like chemicals which lower the freezing point of water. This would help it stay liquid even in Pluto's extreme cold. Scientists haven't directly detected the ocean, but they use gravity data, surface geology, and thermal modeling to support the idea. Future missions could confirm its existence using seismology or radar mapping, which would provide direct clues about what lies below. Pluto joins other icy bodies, like Europa, Enceladus, and Titan as possible hosts of underground oceans. Even in distant frozen regions of the solar system, liquid water may be more common than once thought. This changes how scientists view habitability in extreme environments. An underground ocean on Pluto is unlikely to support life, but it still raises big questions. How long could such an ocean last? How does it interact with the crust? Could Pluto have had a warmer past or more active geology than we imagined? The idea of oceans on distant dwarf planets challenges previous ideas that only inner planets could have geological complexity. It shows that size and distance from the Sun don't always prevent internal activity and liquid water. So even at the fringes of the solar system, Pluto may hide a cold, dark ocean beneath its frozen crust, adding to the list of places where liquid water may still exist long after the formation of the solar system. Saturn's north pole has a perfect hexagonal pattern, and scientists don't fully understand why. At Saturn's north pole, there's a gigantic hexagon-shaped jet stream that circles the pole continuously. This strange six-sided shape was first spotted by the Voyager spacecraft in the 1980s and later studied in detail by the Cassini mission. The hexagon is about 30,000 kilometers wide, larger than Earth. It's a stable and long-lasting feature in the planet's atmosphere. The hexagon is a cloud pattern, not a surface structure. It rotates with the planet and stays mostly in the same place. Winds inside the hexagon move at over 300 kilometers per hour, creating a fast-moving jet stream that curves into a six-sided shape instead of a circle. The reason for this hexagon isn't fully known. It may result from fluid dynamics in Saturn's atmosphere, especially how winds at different latitudes interact. Laboratory experiments with rotating fluids have created similar polygon shapes, supporting this idea. But why Saturn's hexagon is so large and stable remains a mystery. The shape doesn't drift or fade over time. Cassini observed it for over a decade, and the hexagon never disappeared. It also seems locked to Saturn's rotation, meaning it doesn't move independently from the planet's spin. That makes it even more unusual compared to other weather systems. The hexagon has layers, with some parts appearing deeper than others. Infrared images show that the pattern extends far down into the atmosphere, possibly hundreds of kilometers. This suggests it's not just a surface feature, but a deep-seated atmospheric structure. There's also a massive storm in the middle of the hexagon, sitting right at the North Pole. It has its own eye and spiral structure, like a hurricane. The storm and the hexagon may be related, but they don't move in sync. Each has its own wind patterns and behavior. Interestingly, there is no hexagon at Saturn's south pole. That pole has a different type of vortex, more circular and hurricane-like. The absence of a southern hexagon makes the northern one even harder to explain. It may be due to differences in solar heating or internal dynamics. Some theories suggest standing waves in the atmosphere create the shape, similar to patterns seen in other rotating fluids. But no model has perfectly replicated the size, depth, and stability seen on Saturn. It remains one of the most unusual and unexplained structures in the solar system. Researchers continue to study old Cassini data to find more clues. New missions may someday observe the hexagon again and provide better data on wind speeds, temperature variations, and chemical composition. Until then, it stays one of Saturn's biggest mysteries. So far, Saturn's North Pole hexagon is a rare example of geometric precision in nature, appearing not in solid rock or ice, but in fast-moving gas, maintained by forces we still don't fully understand. There is diamond rain on Neptune and Uranus, caused by extreme pressure. The atmospheres of Neptune and Uranus are rich in hydrocarbons like methane, which contains carbon. Deep inside these planets, pressures reach millions of times Earth's atmospheric pressure. At these depths, the pressure is so intense that it crushes carbon atoms into diamond. Scientists believe that under the right temperature and pressure, methane molecules break apart and the carbon atoms reform as crystals of solid diamond. These diamonds then fall like rain through the planet's interior. The process is believed to happen thousands of kilometers below the surface. This diamond rain doesn't happen in the upper atmosphere. It occurs deep in the layers where the pressure is high enough to compress carbon. These conditions don't exist on gas giants like Jupiter or Saturn, which are composed mostly of hydrogen and helium, not methane-rich ices. The idea was first proposed in the 1970s, but gained more attention with lab experiments. Scientists simulated conditions similar to Neptune and Uranus using high-powered lasers. They successfully created diamond crystals by compressing hydrocarbons under extreme conditions. The diamonds likely don't stay intact forever. As they fall deeper into the planet's interiors, they may melt or dissolve in liquid layers. Still, this diamond rain could be continuous, contributing to heat and energy flow inside these ice giants. This process may also help explain why Uranus and Neptune emit less internal heat than Jupiter and Saturn. Diamond formation could trap energy, or the friction of falling diamonds might contribute to heating. The exact effects are still being studied. While it's not possible to collect these diamonds, they form deep inside hostile planetary environments. The concept has real scientific support. It shows how unusual and extreme chemical processes can get in the outer solar system. Some researchers even speculate that Neptune and Uranus might have layers of liquid diamond deeper inside, though this is still theoretical. These environments are so exotic that we're only beginning to understand what might be happening under their clouds. Uranus and Neptune remain poorly explored. No spacecraft has orbited them, so most of what we know comes from Voyager 2 flybys and telescope observations. Future missions may one day confirm diamond formation directly with better instruments. In short, the enormous pressure inside Uranus and Neptune may cause carbon to crystallize and fall like diamond rain, making these distant ice giants home to one of the most exotic weather patterns in the solar system. Venus's atmosphere is so dense that a lander only survives for a few minutes before being crushed. Venus has one of the most extreme atmospheres in the solar system. It's made mostly of carbon dioxide, with clouds of sulfuric acid, and has a surface pressure about 92 times higher than Earth's. That's like being almost a kilometer underwater on Earth, enough to crush most spacecraft quickly. Several missions have tried to land on Venus. The Soviet Venera landers in the 1970s and 1980s were the only ones to successfully reach the surface and send back data. The longest any of them lasted was about 2 hours, with most lasting less than an hour due to the crushing pressure and intense heat. At the surface, Venus is incredibly hot, about 465 degrees Celsius, 869 degrees Fahrenheit. Hotter than Mercury, even though Venus is farther from the Sun. The thick atmosphere traps heat through a runaway greenhouse effect, making it the hottest planet in the solar system. Most electronics and materials fail quickly in these conditions. Venus's dense air is not just a pressure problem, it also slows descent. Parachutes are used at high altitudes, but lower down, spacecraft fall slowly due to thick atmospheric drag. Once on the ground, they face both extreme heat and corrosive chemicals, which eat away at instruments. The clouds of sulfuric acid start around 50 kilometers above the surface. While the air is cooler up there, the acidity is dangerous for sensors and optics. Any mission must be protected against chemical corrosion and heat damage at multiple levels. Because of these harsh conditions, Venus landers need thick shielding and powerful cooling systems. However, these add weight, which makes it harder to send complex landers. Most missions focus on orbiters or high-altitude balloons, which avoid the harshest parts of the atmosphere. Future missions like NASA's Veritas and Da Vinci plan to explore Venus more safely. Da Vinci will send a probe that descends through the atmosphere, measuring temperature, pressure, and composition. It won't survive on the surface, but it will send back critical data during the fall. There are also proposals for high-temperature electronics that could survive longer on the surface. Materials like silicon carbide might let future landers operate for hours or even days on Venus, but these technologies are still in development. Venus is similar in size to Earth, but its environment is much more extreme. The thick atmosphere not only causes pressure problems, but also blocks visible light, making it hard to see the surface from orbit. Radar mapping is needed to build images of Venus's terrain. In short, Venus crushes most spacecraft in minutes due to extreme pressure, heat, and acidity. It's one of the most hostile places to land in the solar system, and yet one of the most scientifically valuable. Titan, Saturn's moon, has rivers, lakes, and rain, but all made of liquid methane. Titan is Saturn's largest moon, and it has a surface covered with rivers, lakes, and even seas. But instead of water, they are made of liquid methane and ethane. At Titan's extremely low temperatures, methane behaves like water does on Earth. It evaporates, forms clouds, and rains back down. This creates a full methane cycle. Titan has seasons, and its weather changes over time. Scientists have observed storms and rainfall in different regions, depending on the season. Dark streaks across its surface suggest recent rainfall events. Radar images show lakes mostly near the poles, especially the North Pole. Some of these lakes are hundreds of kilometers wide. One of the most striking features is Kraken Mare, a sea of liquid methane bigger than the Great Lakes combined. The Cassini spacecraft found that this sea is at least 300 meters deep in places. Titan also has islands that may appear and disappear, possibly due to floating chunks of ice. There's also evidence of wave activity on these methane seas. Despite how alien this sounds, Titan is one of the most Earth-like worlds ever studied in terms of landscape and surface processes. It has valleys carved by flowing liquid, drainage systems, and even what looks like deltas. But everything happens in a much colder environment, with methane replacing water. Titan's surface temperature is around -179 degrees Celsius. At that temperature, water becomes as hard as rock, and methane becomes a flowing liquid. Its dense atmosphere, mostly made of nitrogen, is thicker than Earth's. That means Titan has weather, wind, and cloud formations. It even has sand dunes, shaped by those winds. Cassini also discovered lightning-like discharges, suggesting that Titan has atmospheric electricity. Combined with organic molecules in the atmosphere, this makes Titan one of the most chemically interesting places in the solar system. Scientists believe that prebiotic chemistry could happen there. It's a laboratory for studying conditions that might lead to life. Titan's sky is orange due to a thick haze of complex hydrocarbons. The haze is so dense that the surface is not visible in visible light. That's why Cassini used radar to map it. In the future, a mission called Dragonfly will send a drone to fly across Titan's surface. It's planned to launch in 2028. Titan also shows signs of a subsurface ocean beneath its icy crust. This ocean would be made of liquid water, possibly mixed with ammonia. If it exists, it could be a second habitat for life on Titan. One environment is based on methane at the surface and the other on water below. Titan is the only moon in the solar system known to have stable liquid on its surface. The combination of atmosphere, liquid cycles, and complex chemistry makes it unique. It's one of the top targets for future exploration. Scientists hope to understand both planetary evolution and the ingredients for life by studying it. No other moon has shown this level of meteorological and geological activity. Titan is not just a frozen rock, it's a dynamic, active world. And it's the only known body besides Earth where rain falls and fills lakes. But unlike Earth, it's not water that drives the cycle. It's methane. Mercury is slowly shrinking over time. Mercury, the smallest planet in the solar system, is getting even smaller. Over billions of years, it has contracted as its interior cools. The planet's core takes up most of its volume, and as it loses heat, it solidifies and shrinks. This causes the outer layers to wrinkle and fold, forming cliffs and ridges on the surface. These cliffs, called lobate scarps, can be hundreds of kilometers long and several kilometers high. They're visible from space and show that the crust was pushed together. This is direct evidence that the planet is shrinking. Some of these features appear to be geologically recent, meaning Mercury may still be shrinking today. The shrinking is estimated to be around 7 kilometers in diameter over the planet's history. While that seems small on a planetary scale, it creates massive deformation on the surface. The process is slow, but continuous. Mercury doesn't have tectonic plates like Earth, so this shrinking happens in a simpler, one-piece fashion. The core of Mercury is unusually large compared to its total size. It likely makes up 85% of the planet's radius. As the core cools and contracts, it pulls the crust inward. That movement breaks the surface, forming large, step-like structures. The surface looks like it has folded in on itself. Mercury doesn't have an atmosphere thick enough to erase these features. There's no erosion, no weather, and no plate tectonics to flatten the landscape, so the scarps stay visible for billions of years. They are permanent markers of how the planet has changed over time. Some spacecraft images show smaller scarps cutting across younger impact craters, meaning the shrinking continued after the craters formed. This shows that the process is still active. Most planetary surfaces don't show that level of continuous internal change without external forces like volcanism or tectonics. The planet's closeness to the Sun increases the thermal stress on its surface. Temperature swings range from negative 170 degrees Celsius at night to plus 430 degrees Celsius during the day. These extreme changes cause the crust to expand and contract regularly. Over time, that adds to the stress and deformation. There's no evidence of current volcanism on Mercury, but many of its basins are volcanic in origin. This supports the idea that its interior was once very hot and active. As the planet lost its internal heat, the contraction became the main driver of geological change. The shrinking of Mercury is a planet-wide phenomenon. Unlike Mars, which lost activity early and became geologically dead, Mercury still shows signs of slow but ongoing internal evolution. It's one of the few rocky bodies that may still be physically changing today. Mercury is often overlooked due to its small size and lack of atmosphere. But its slow shrinkage offers valuable insights. It helps scientists understand how rocky planets evolve over billions of years. Even a small planet close to the Sun can have a complex and active geological history. The Moon is slowly moving away from Earth. The Moon is increasing its distance from Earth by about 3.8 centimeters per year. This has been measured with high precision using laser reflectors left by Apollo missions. The reason is tidal interaction. Earth's gravity pulls on the Moon, and the Moon pulls back on Earth's oceans, creating tides. This tidal friction transfers rotational energy from Earth to the Moon. As a result, the Moon speeds up slightly in its orbit and moves farther away. At the same time, Earth's rotation slows down gradually. This means that days on Earth are getting longer over time. Hundreds of millions of years ago, Earth had shorter days and a closer Moon. During the age of the dinosaurs, a day lasted about 23 hours, and the Moon was much larger in the sky. If this trend continues, Earth's days will eventually reach over 25 hours in the distant future. The Moon's movement also affects Earth's axial tilt stability. Right now, the Moon helps keep Earth's tilt relatively stable, which regulates the climate. If the Moon were much farther away or disappeared, Earth's tilt could shift more drastically. This could lead to more extreme climate changes over time. This process is not unique to our Moon. Tidal evolution happens in other systems too. But in Earth's case, the Moon is unusually large compared to its planet, which makes the effect more significant. That's why Earth has such strong ocean tides and long-term rotational changes. Over billions of years, this interaction has transformed the Earth-Moon system. In the distant past, the Moon orbited Earth much faster and was more geologically active. Today, it's tidally locked, always showing the same face to Earth. That locking is the result of gravitational resonance. Eventually, if nothing else interferes, the system could reach a point called tidal equilibrium. In that case, both Earth and Moon would show the same face to each other, and Earth's rotation would match the Moon's orbital period. But this would take tens of billions of years, and the Sun will expand before that happens. Even though the change is slow, the cumulative effects are large. The Moon has moved tens of thousands of kilometers away from Earth since it formed. That distance has influenced everything from eclipses to the speed of Earth's rotation. It's one of the most well-measured long-term changes in the solar system. This recession of the Moon is also used to understand orbital mechanics and system evolution in exoplanets. Studying how our Moon behaves over time helps model other planetary systems. It's a real-world example of gravitational interaction over vast timescales. The Moon's drift is invisible on a day-to-day basis, but over millions of years, it changes Earth's rotation, tides, and sky. It's a constant, silent motion that has shaped life on Earth in ways we're still discovering. Jupiter's magnetic field is so strong it affects its moons. Jupiter has the strongest magnetic field of any planet in the solar system. It's about 20,000 times stronger than Earth's magnetic field. This magnetic field traps charged particles from the solar wind and accelerates them. These particles form intense radiation belts around the planet. The radiation is powerful enough to damage spacecraft electronics. Jupiter's magnetic field extends far beyond the planet itself. It forms a huge structure called the magnetosphere, which is millions of kilometers across. This magnetosphere even reaches past some of Jupiter's moons. As a result, these moons are constantly exposed to radiation. Some of them experience electromagnetic interactions with Jupiter. Io, one of Jupiter's largest moons, is a prime example. As it moves through the magnetic field, it generates an electric current. This interaction creates auroras at Jupiter's poles and contributes to plasma clouds around the planet. Io also gets bombarded by charged particles, which affect its surface and atmosphere. Europa, another moon, is also affected. The magnetic field passes through its icy surface and may induce currents in its subsurface ocean. This is one of the reasons scientists believe the ocean is salty and conductive. Magnetic data helped confirm the existence of liquid water beneath the ice. Ganymede, Jupiter's largest moon, is the only moon in the solar system with its own magnetic field. This magnetic field interacts directly with Jupiter's. The overlapping fields create complex regions of magnetic reconnection. These can cause variations in auroras and affect the space environment around Ganymede. The intensity of Jupiter's magnetic field creates a hazardous zone for spacecraft. Missions like Galileo and Juno had to be carefully planned to avoid prolonged exposure. Radiation levels near the planet are high enough to destroy unshielded electronics within hours. Protective shielding is necessary for any probe operating nearby. Jupiter's magnetosphere also acts as a barrier, deflecting most solar wind particles. But the trapped particles inside can become extremely energetic. This trapped radiation plays a key role in shaping the surfaces of nearby moons. It can even erode thin atmospheres, like the one found on Europa. Because of the field's strength, it also generates powerful radio emissions. These can be detected from Earth and provide useful data. The emissions vary depending on Jupiter's rotation and the positions of its moons. This radioactivity is one of the first things noticed by early space observatories. Jupiter's field is generated by its liquid metallic hydrogen core. Unlike Earth, which has a solid iron core, Jupiter's magnetic field comes from this exotic state of hydrogen. The planet's fast rotation also contributes to the dynamo effect. This combination creates a massive and complex field. Jupiter's magnetic environment affects everything in its system, from small particles to entire moons. It's a dominant force in that region of space. Any mission to the Jovian system must take this magnetic field into account. It's not just strong, it's one of the most powerful forces in the solar system. Triton, Neptune's moon, orbits in the opposite direction of its planet's rotation. Triton is the largest moon of Neptune, and it has a retrograde orbit. This means it orbits opposite to the direction Neptune spins. Most large moons in the solar system follow the same direction as their planet's rotation. Triton's orbit is the exact reverse, which makes it extremely unusual. This retrograde motion suggests that Triton was not formed around Neptune. Instead, scientists believe it was captured by Neptune's gravity. Triton may have been part of a binary system that passed too close. One object was ejected, and the other, Triton, got pulled in. This explains its strange path. Capturing a moon this size is rare. Triton is bigger than Pluto, making it one of the largest objects in the outer solar system. After its capture, its orbit would have been unstable. Over time, it became more circular due to gravitational interactions, but it kept its retrograde direction. This backward orbit creates tidal forces between Triton and Neptune. These forces are gradually shrinking Triton's orbit. One day, Triton may get so close to Neptune that it will be torn apart. When that happens, it could form a new ring system around the planet. Triton has other unusual features. Its surface is extremely cold, around -235 degrees Celsius and covered with nitrogen ice. Despite the cold, it shows geological activity. Voyager 2 observed cryovolcanoes, which release icy material instead of lava. This suggests Triton has internal heat, possibly from tidal friction. The surface of Triton is also relatively young. It has few impact craters, meaning it is geologically active. Geysers of nitrogen gas were seen shooting several kilometers into space. These are signs that the surface is being renewed. For a moon so far from the Sun, this is unexpected. Triton also has a thin atmosphere made mostly of nitrogen. The atmosphere changes as Triton moves along its orbit, influenced by solar heating. This affects the pressure at the surface and may trigger surface changes. The atmosphere is too thin to support flight, but it plays a role in surface erosion. Because of its orbit and composition, Triton is often compared to Kuiper Belt objects. Its similarities to Pluto support the idea that it originated in that region. Capturing such an object helps explain the diversity of Neptune's moons. It also shows how chaotic the early solar system was. Voyager 2 is the only spacecraft that has flown by Triton. It passed in 1989 and took the only close-up images we have. No other mission has returned since. Scientists consider Triton a priority for future exploration due to its unique origin and activity. Triton's retrograde orbit is solid evidence that it was captured. It's one of the clearest examples of a planet pulling in a large object from elsewhere. This process changes the dynamics of an entire planetary system. Triton is more than a moon. It's a captured world. The asteroid belt is mostly empty space. The asteroid belt lies between Mars and Jupiter, and it's often imagined as a crowded field of rocks. But in reality, it's mostly empty space. The asteroids are separated by millions of kilometers, and collisions are rare. A spacecraft flying through the belt would most likely see nothing nearby. The total mass of all the asteroids combined is less than 5% of the Moon's mass. Even the largest object, Ceres, is only about 950 kilometers in diameter. Other major bodies include Vesta, Pallas, and Hygiea, but most are small. The rest are tiny fragments left over from the early solar system. The belt didn't come from a destroyed planet. Instead, it's made of material that never formed a planet. Jupiter's gravity prevented the objects from sticking together. It stirred up the region, causing collisions that broke larger objects into smaller pieces. This kept the belt in a fragmented state. There are hundreds of thousands of known asteroids and likely millions of smaller ones. But even so, the space between them is vast. If you were standing on one asteroid, you would probably not see another one nearby. Most of them are far apart, spread across a wide region. The main belt stretches from about 2.1 to 3.3 astronomical units from the Sun. That's a region over 300 million kilometers wide. Even with thousands of objects in that space, the density is extremely low. The idea of spacecraft dodging asteroids is more science fiction than reality. Most asteroids are made of rock, metal, or carbon-rich compounds. Their compositions vary depending on where they formed. Some are leftovers from the inner solar system, others from farther out. Studying them helps us understand the early solar system's building blocks. Missions like Dawn have visited Vesta and Ceres, providing detailed data. Other spacecraft like OSIRIS-REx and Hayabusa 2 have returned samples from near-Earth asteroids. These missions help refine our understanding of how the belt evolved. They also show that the belt is a diverse and active region despite being sparse. There are also asteroid families, which are groups of fragments from a larger parent body. These families move in similar orbits and have similar compositions. Their existence supports the idea that collisions were common in the past, but today most of the belt is quiet. Some asteroids in the belt are considered potential resources for future missions. They may contain metals, water, and other materials useful for space operations. However, mining them would require traveling through vast, empty regions. Logistics remain a major challenge. The asteroid belt is not a dense field of debris. It's a structured, stable region of scattered objects. Its emptiness surprises many people, but it's exactly that emptiness that allowed spacecraft to cross it multiple times, safely and without incident. There's a mysterious zone between Mars and Jupiter that could have been a planet that never formed. Between the orbits of Mars and Jupiter lies a region known as the asteroid belt. Some scientists believe this area could have formed a planet early in the solar system's history. However, the strong gravitational influence of Jupiter disrupted the process. Instead of forming one large body, the material remained fragmented. That's why it's sometimes referred to as a failed planet zone. The total mass of all the asteroids in the belt is very small, only a fraction of the Moon's mass. This suggests that most of the original material was either ejected or incorporated into other bodies. It's possible that this region once had enough raw material to form a planet, but the constant tug of Jupiter's gravity made the orbits unstable. Collisions likely destroyed anything that started to grow large. This idea is supported by the existence of asteroid families, which are groups of fragments from once larger objects. These fragments share similar orbits and compositions. Some may be cores or mantles of larger protoplanets that were broken apart. That suggests that at least partial planetary formation may have happened, but full development into a stable planet was prevented. One theory is that a protoplanet may have formed and later been shattered, but there's no clear evidence of a single destroyed planet. Instead, the area shows signs of long-term gravitational disturbance. That's why most researchers support the idea of planet formation being interrupted rather than reversed. The belt contains various types of asteroids: carbon-rich, C-type, silicate, S-type, and metal-rich, M-type. These compositional differences show that material from different parts of the early solar system ended up here. It's a kind of cosmic graveyard for leftover building blocks, but it also preserves clues about what failed to become a planet. Some missions, like Dawn, studied large asteroids like Vesta and Ceres, which may represent what early protoplanets looked like. Ceres is even classified as a dwarf planet. It's the closest example we have of a body that might have become a full planet under different conditions. But even Ceres is too small to be called a true planet. Jupiter's role is crucial. Its massive gravity caused orbital resonances in the asteroid belt. These resonances create gaps and areas of instability where material was either thrown out or collided at high speeds. These events prevented large-scale accretion from taking place. Essentially, Jupiter blocked planetary formation in that zone. Some past models proposed the existence of a lost planet named Triton that may have existed there, but modern science doesn't support the idea of a single destroyed planet. Instead, current data favors the concept of a disrupted formation phase. The asteroid belt likely never formed a planet at all. Today, the region remains stable but still scattered. It's been crossed by multiple spacecraft without incident. Its low density and wide spacing confirmed that a planet is unlikely to form now. Too much mass has been lost, and too many forces still prevent accretion. The idea of a missing planet is mostly used to describe what could have happened under different conditions. The asteroid belt is not the remains of a world, it's the result of a process that was cut short before completion. It's a window into the early chaotic days of planet formation. Uranus's moons orbit in a tilted plane, as if the planet was knocked over. Uranus rotates on its side with an axial tilt of about 98 degrees. This means the planet is almost lying down relative to its orbit. As a result, its moons orbit in that same tilted plane, following the planet's unusual orientation. It's the only planet with this extreme tilt. The most accepted theory is that a massive collision knocked Uranus over in its early history. Unlike other planets, Uranus's poles point nearly at the Sun during parts of its orbit. This causes extreme seasonal changes that last over 20 years. Its moons, including Titania, Oberon, Ariel, Umbriel, and Miranda, follow this tilted rotation. They orbit around the planet's equator, which is now sideways. Everything in the Uranian system is affected by this tilt. The moons are relatively small and icy, showing signs of past geological activity. Some have valleys, cliffs, and possible cryovolcanoes. The tilt affects how sunlight hits the moons during their orbits, causing long periods of darkness and light. The lighting conditions can last for decades, depending on their position. Miranda, one of the smallest moons, has one of the weirdest surfaces in the solar system. It has massive cliffs, jumbled terrains, and structures that don't match any known pattern. Some researchers believe this moon was shattered and reassembled. Its chaotic look could be linked to the collision that tilted Uranus. The collision theory suggests that a massive protoplanet or icy body hit Uranus during the early solar system. The impact would have been strong enough to alter its spin axis without destroying the planet. It may have also influenced the formation of its moons. Their orbits match Uranus's new tilt, indicating they formed after the event. Uranus's magnetic field is also tilted and offset from the planet's center. This irregularity might also be a result of the collision. The planet's interior is less understood, but this magnetic shift could suggest layered structures or a shifted core. These factors combine to make Uranus one of the most asymmetric planets. Voyager 2 is the only mission to have flown by Uranus. In 1986, it captured basic data but didn't provide high-resolution images of the moons. Most of what we know comes from that flyby and Earth-based telescopes. Future missions could reveal much more about the moon's composition and internal structure. The moons orbit relatively close to Uranus, all within a compact system. Because they follow the planet's tilted equator, their paths look unusual when viewed from above the solar system's plane. Instead of circling upright, they move around almost vertically. This makes the Uranian system completely different from others. Some models suggest Uranus may have had a ring system before the impact, which got disrupted. The current rings are faint and dark, and might be remnants of that original system. If the moons also formed from debris, their alignment would match the planet's new orientation. This supports the post-impact formation idea. Uranus and its moons provide an example of how a single massive event can reshape an entire planetary system. The tilted axis, unusual seasons, magnetic irregularities, and moon orbits all point to a violent beginning. It's a system shaped by one major impact, and the effects are still visible today. The entire solar system orbits the Milky Way in a cycle that lasts 225 million years. The solar system is not stationary. It orbits around the center of the Milky Way galaxy. This journey takes about 225 to 250 million years to complete. That means the last time the solar system was in its current position, dinosaurs didn't exist. This orbit is called the galactic year. The Sun, along with its planets, moves at an average speed of about 828,000 kilometers per hour. Even at this speed, the journey is incredibly long due to the galaxy's size. The Milky Way is about 100,000 light-years wide, and the Solar System is located roughly 27,000 light-years from the center, where on one of the spiral arms. The orbit isn't a perfect circle. It's slightly elliptical and also involves vertical motion, where the Solar System moves above and below the galactic plane. This oscillation may happen every 30 to 40 million years. Some studies suggest this vertical motion could be linked to mass extinction cycles, but the evidence is not conclusive. The gravitational forces that keep the Solar System in orbit come from the galactic core, where a supermassive black hole resides. However, most of the galaxy's mass is in the form of dark matter, which influences the orbit without being directly observed. This mass holds the spiral arms and stars together. Our motion through the galaxy is affected by the movement of nearby stars and interstellar clouds. These interactions don't disturb planetary orbits, but they may send objects from the Oort cloud inward. This could increase the number of comets entering the inner solar system during certain periods. The solar system travels with a group of stars known as the local standard of rest. We move relative to this group and also relative to other galactic structures. Over time, the view of the night sky changes as the solar system passes through different parts of the galaxy. Constellations are not permanent. Even though the galaxy is full of stars, space is still incredibly vast. The solar system's orbit doesn't lead to frequent stellar encounters. Close approaches with other stars are very rare, but they can happen on million-year timescales. These events could slightly perturb comets and distant objects. The solar system is currently moving toward a region called the Hercules Corona Borealis Great Wall, one of the largest known structures in the universe. However, this motion is part of multiple larger-scale movements, including the motion of the entire galaxy toward the Virgo supercluster. The concept of a galactic year is useful for understanding geological and evolutionary timelines. Major shifts on Earth, including continental drift and extinction events, have occurred during different points of this long orbit. The solar system has completed only about 20 full orbits in its entire history. Even though we don't feel it, the solar system is constantly moving through space at high speeds. Our position in the galaxy is always changing. Over millions of years, this movement shapes the environment around us, both locally and on a cosmic scale. Ceres, a dwarf planet, has bright salt patches on its surface. Ceres is the largest object in the asteroid belt and is classified as a dwarf planet. It has a diameter of about 950 kilometers and is mostly made of rock and ice. One of its most unusual features is the presence of bright white spots on its surface. These spots are highly reflective and clearly visible in spacecraft images. They are made of salt deposits, primarily sodium carbonate. These salt patches are concentrated in Akator crater, a large impact basin. The central region of the crater, called Soralia Focula, is the brightest. Scientists believe these salts were left behind by briny water that seeped up from below the surface. As the liquid evaporated, it left salt deposits behind. This process is similar to what happens in dry lake beds on Earth. The Dawn spacecraft studied Ceres in detail from 2015 to 2018. It confirmed that the bright material was not ice, but salt left by recent cryovolcanic activity. That means Ceres may still have some internal heat. The upwelling of brine could have happened within the last few million years. It's considered geological young for a body in the asteroid belt. Other salt patches were also found in different regions of Ceres. This suggests that the subsurface has pockets of liquid brine. These could occasionally reach the surface through cracks caused by impacts or stress. Even though Ceres looks inactive from a distance, it shows signs of ongoing internal processes. Some models suggest that Ceres has a muddy, icy mantle and a crust made of hydrated materials. The salts may originate from a layer of brine reservoirs beneath the surface. Radioactive decay could provide enough heat to keep these reservoirs liquid. This would explain how salt water was able to reach the surface. Ceres is the only object in the asteroid belt with confirmed water-related activity. Its low gravity and cold temperatures make it surprising that liquid water could exist at all. But salt lowers the freezing point of water, allowing it to remain liquid longer. This is key to explaining the recent movement of brine. The presence of salts may also suggest chemical reactions that could support prebiotic chemistry. While Ceres is not considered a candidate for life, it shares characteristics with icy moons that are. Studying Ceres helps scientists understand how ocean worlds evolve, especially when located far from the Sun. Ceres's low density indicates that a significant portion of it is ice. This makes it different from rocky asteroids nearby. Its surface is heavily cratered, but the bright spots stand out sharply. They appear in high-resolution images as concentrated white deposits. These features change how scientists think about activity in small, cold bodies. Unlike other dwarf planets like Pluto or Ceres, Ceres lies in the inner solar system, making it more accessible for future missions. Its surface composition and geology make it a priority target for sample return or lander missions. A mission could directly analyze the salt deposits for more detailed chemistry. Ceres shows that even small bodies in the asteroid belt can be active and complex. The salt patches are not just surface features, they are evidence of subsurface movement. That makes Ceres not just a leftover rock, but a body with ongoing geological behavior. There are more moons in the solar system than planets, and some have geological activity. The solar system has 8 planets, but more than 290 confirmed moons orbiting planets. Some gas giants like Jupiter and Saturn each have over 90 moons. These moons come in various sizes and types. Some are small and irregular, while others are larger than Mercury. Many of them are geologically inactive, but a few show remarkable activity. Io, a moon of Jupiter, is the most volcanically active body in the solar system. It has hundreds of volcanoes, some of which erupt constantly. These eruptions are driven by tidal heating caused by gravitational interactions with Jupiter and neighboring moons. The surface is constantly being reshaped by lava flows. Io proves that moons can be more active than planets. Europa, also orbiting Jupiter, has a smooth, icy surface and likely an ocean of liquid water beneath it. Its ice shell may be just a few kilometers thick, and cracks in the surface suggest movement. Geysers of water vapor have been detected near its south pole. These are signs of internal heat and subsurface activity. Enceladus, a moon of Saturn, also has water geysers. It ejects material from cracks in its icy surface, creating a plume that extends into space. The Cassini spacecraft flew through this plume and detected organic molecules. Enceladus has a subsurface ocean and is considered one of the best candidates for extraterrestrial life. Triton, Saturn's largest moon, has rivers, lakes, and seas of liquid methane. Its dense atmosphere allows for weather systems and seasonal changes. While it's too cold for liquid water on the surface, it may have a water-ammonia ocean deep below. Geological features like dunes and cryovolcanoes show active surface processes. Triton, Neptune's largest moon, is geologically active despite being extremely far from the Sun. It has cryovolcanic geysers and a relatively young surface. Its backward orbit indicates it was captured by Neptune's gravity. Tidal forces from that capture may still generate internal heat. Many smaller moons are believed to be captured asteroids, especially those with irregular shapes and distant orbits. These are usually inactive and have heavily cratered surfaces. However, their composition can still reveal clues about the early solar system. Some are rich in ice, others in metals or carbon compounds. The total number of moons keeps growing as new ones are discovered with better telescopes. In recent years, dozens of new moons have been found around Jupiter and Saturn. Most of these are very small and hard to detect, but they still count as natural satellites. Some moons may contain materials useful for future space exploration. Water ice can be used for drinking, fuel, or oxygen. That makes some moons important not just scientifically, but practically for missions. Moons like Europa, Titan, and Enceladus are high on the list for exploration. Moons are no longer seen as passive objects. Many of them are dynamically active, with atmospheres, oceans, or volcanoes. They show that planetary activity isn't limited to planets. Some of the most interesting places in the solar system are orbiting something else. Earth shares its orbit with Trojan asteroids that travel with us, unseen to the naked eye. Trojan asteroids are small bodies that share a planet's orbit around the Sun. They stay in stable gravitational zones called Lagrange points, specifically L4 and L5. These points are located 60 degrees ahead and behind the planet in its orbit. Earth has several known Trojan asteroids in these positions. They're hard to see because of their position relative to the Sun. The first Earth Trojan was discovered in 2010 and named 2010 TK7. It is about 300 meters in diameter and orbits near Earth's L4 point. It moves in a tadpole-shaped path around the stable point, never straying far. Because it's close to the Sun's glare, it took a long time to detect. More may exist, hidden in the same way. Trojan asteroids are also found around Jupiter, Neptune, and Mars. Jupiter has the most, with over 10,000 known Trojans. These objects are stable over millions of years. Earth's Trojans are fewer, possibly because of its location or observational limits. Some of them could have existed since the early solar system. These asteroids are not dangerous to Earth. They stay in stable orbits and do not cross paths with our planet. Their distance and positioning prevent close encounters. Some are considered targets for future missions because of their accessibility and orbital stability. The Trojans follow the same general orbit as Earth, but remain well ahead or behind. They complete one orbit around the Sun at the same speed as Earth. This synchrony keeps them in position due to the combined gravitational pull of the Sun and Earth. It's a natural balance point. Detecting them is difficult because they are always close to the Sun's direction from Earth's perspective. That makes observations challenging using ground-based telescopes. Specialized space missions or instruments with wide viewing angles are better suited. This is why more Trojans may exist but remain undiscovered. The study of Trojan asteroids can provide information about solar system formation. They may contain primitive materials from the early solar nebula. Their orbits preserve their conditions, making them good time capsules. Sampling them could reveal the building blocks of terrestrial planets. NASA has planned a mission called NEO-Surveyor, which may detect more of these objects. It's part of a broader effort to map near-Earth asteroids. Other planned missions could visit Trojans to analyze their composition directly. These efforts are key to understanding co-orbital dynamics. Trojan asteroids can also orbit other planets' Lagrange points, including Mars and Neptune. Saturn and Uranus may have temporary ones, but their orbits are less stable. The phenomenon is not unique to Earth, but follows universal gravitational rules. Any large planet can have them under the right conditions. Though invisible to the naked eye, these Trojans are part of Earth's broader orbital environment. They orbit with us, largely unnoticed, yet stable for long periods. Their existence shows that our orbit is more complex than just one planet circling the Sun. We're not alone on this path. Some comets come from the edges of the solar system and take thousands of years to return. Long-period comets originate from the Oort cloud, a distant region that surrounds the solar system. This cloud may extend up to 100,000 astronomical units from the Sun. Comets from this area take thousands or even millions of years to complete one orbit. Their paths are often highly elongated. Many only pass near the Sun once in recorded history. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of long-period comets. These objects often appear suddenly and have no known source within the inner solar system. Their arrival angles suggest a spherical cloud of icy bodies far beyond Pluto. It's considered the outermost region of the solar system. When a comet from the Oort cloud is disturbed by nearby stars, gravity from the Milky Way, or internal shifts, it may fall toward the Sun. As it approaches, solar heat causes its ice to vaporize, forming a visible coma and tail. These are the classic bright comets that become visible from Earth. Most fade away after a single pass. These long-period comets have orbits that range from hundreds to millions of years. Some famous examples include Comet Hale-Bopp and Comet C/2011 L4 Pan-STARRS. Their highly eccentric orbits make them unpredictable. They often pass through the inner solar system without ever being seen again in human lifetimes. Comets are made of ice, dust, and rock, and are considered leftovers from the early solar system. Those in the Oort cloud likely formed near the giant planets but were pushed outward. Their current positions are the result of gravitational scattering over billions of years. They remain frozen in deep space until something changes their path. When they enter the inner solar system, they provide valuable scientific data. The material in comets is often unaltered since formation, giving insight into the early solar system. Missions like Rosetta, which landed on a comet, have revealed complex molecules. Some comets may carry the organic ingredients that seeded planets. Because of their rare visits, long-period comets are difficult to study in detail. They usually move fast and stay visible for only a few weeks. Astronomers track them using telescopes and compute their paths using orbital mechanics. If one is heading near Earth, it becomes a high-priority observation target. Most of these long-period comets pose no threat to Earth. Their paths are far and predictable once calculated. However, a large object coming from the Oort cloud would be hard to detect early. That's why new surveys aim to scan the sky for incoming comets and near-Earth objects. Not all long-period comets survive their journey. Some break apart near the Sun due to thermal stress. Others collide with planets or disappear into interstellar space. A few get captured into shorter orbits, becoming new periodic comets. These changes depend on gravity from planets like Jupiter. Long-period comets are a reminder that the solar system doesn't end with Neptune or Pluto. A vast region of icy bodies exists far beyond, mostly unseen. When one of these ancient travelers enters the inner system, it brings with it clues from the solar system's formation. 23. Solar winds are so intense they shape Earth's magnetic field. The solar wind is a constant flow of charged particles, mainly electrons and protons, released by the Sun. These particles travel through space at speeds of up to 800 kilometers per second. When they reach Earth, they interact with our magnetosphere, the magnetic field that surrounds the planet. This interaction causes the magnetosphere to stretch and change shape. On the side facing the Sun, the magnetosphere is compressed. On the opposite side, it's extended into a long tail that reaches millions of kilometers into space. These changes happen in response to variations in the solar wind's speed and density. The stronger the solar wind, the more the magnetosphere is distorted. The solar wind is not constant. It can become much stronger during solar storms or coronal mass ejections, CMEs. These events release enormous bursts of solar material. When they hit Earth's magnetic field, they can cause geomagnetic storms. These storms affect satellites, communications, and power grids. The auroras, northern and southern lights, are caused by solar wind particles entering Earth's upper atmosphere. They follow the magnetic field lines toward the poles where they collide with gas molecules. These collisions release energy in the form of light. The colors depend on the type of gas involved. Earth's magnetic field acts as a shield, but it doesn't block all solar wind particles. Some particles get trapped in the Van Allen radiation belts, regions of charged particles around Earth. These belts can pose a hazard to satellites and astronauts. Their shape and intensity vary with solar wind conditions. The interaction between solar wind and the magnetosphere creates currents in Earth's ionosphere. These can induce electrical currents in the ground, especially in long metal systems like pipelines and power lines. This is why strong solar storms can damage infrastructure on Earth. Monitoring the solar wind is essential for space weather forecasting. Satellites like ACE and DSCOVR provide real-time data. This allows agencies to issue warnings for geomagnetic storms. These warnings can help prevent or limit damage to sensitive systems. The magnetosphere also plays a role in atmospheric retention. Planets without magnetic fields, like Mars, have lost much of their atmosphere to the solar wind. Earth's field helps prevent that kind of loss. It's one reason our planet remains habitable. The shape and strength of Earth's magnetic field are constantly changing. Solar activity is one factor, but internal processes in Earth's core also play a role. Still, solar wind is the primary external force that sculpts the magnetosphere's outer boundary. The constant interaction between the solar wind and Earth's magnetic field creates a dynamic system. It protects the planet, generates auroras, and occasionally causes disruptions. This ongoing process is a key part of Earth's relationship with the Sun. The heliosphere is a protective bubble created by the Sun that shields us from external radiation. The heliosphere is a vast region of space influenced by the solar wind and the Sun's magnetic field. It forms a kind of bubble around the solar system. Inside this bubble, solar wind particles dominate. Outside of it, space is filled with galactic cosmic rays and particles from other stars. The heliosphere acts as a shield that blocks or deflects some of this external radiation. It protects the planets from the full intensity of cosmic rays, which are high-energy particles from outside the solar system. This protective effect is especially important for the inner planets. Without it, Earth would receive more harmful radiation. The boundary of the heliosphere is called the heliopause. This is the point where the solar wind slows down and can no longer push back against interstellar particles. Beyond the heliopause lies interstellar space. The Voyagers 1 and 2 spacecraft have both crossed this boundary, providing direct data. Before reaching the heliopause, the solar wind passes through the termination shock. This is where the solar wind slows down suddenly due to resistance from the interstellar medium. The region between the termination shock and the heliopause is called the heliosheath. It's a turbulent zone full of mixed particles. The shape of the heliosphere is not a perfect sphere. It's distorted by the movement of the solar system through the galaxy. Some models suggest a comet-like shape, with a rounded front and a trailing tail. The Sun's magnetic field helps hold this structure together. It changes depending on the solar activity cycle. The strength of the heliosphere varies with solar activity. During periods of high solar activity, it expands. When the Sun is quieter, it contracts slightly. These changes affect how much cosmic radiation enters the solar system. Astronauts and satellites are more exposed during weak periods. The heliosphere doesn't block all cosmic rays. Some high-energy particles can still penetrate it and reach the inner solar system. However, the overall exposure is significantly reduced. This makes the heliosphere one of the key protective layers for life on Earth. Understanding the heliosphere is essential for planning long-term space missions. Outside its protection, radiation becomes a serious threat. That's why missions to Mars and beyond require advanced shielding or planning during solar maximum, when the heliosphere is stronger. The heliosphere is created by the continuous output of solar wind and magnetic energy. It's not a static structure, but a dynamic boundary. Changes in the Sun's behavior directly influence its size and shape. Studying these changes helps scientists understand both solar and galactic environments. The heliosphere is the outermost layer of the Sun's influence. It separates our solar system from the rest of the galaxy's radiation. Without it, the conditions in the inner solar system, including on Earth, would be much less stable and much more dangerous. The darkest planet in the solar system is Uranus. It reflects very little light. Uranus is known for its pale blue-green color, but it is actually one of the least reflective planets in the solar system. Its albedo, which measures reflectivity, is around 0.3, meaning it reflects only about 30% of the sunlight it receives. This is lower than most gas giants, especially compared to Jupiter and Saturn. It makes Uranus the darkest of the major planets in terms of visible reflectivity. The reason for this low reflectivity is still not fully understood. Scientists believe it may be due to a thick haze layer in the planet's upper atmosphere. This haze absorbs sunlight instead of reflecting it. Unlike Neptune, which has similar composition but a more vivid color, Uranus appears more dull and muted in images. Uranus's atmosphere is composed mainly of hydrogen, helium, and methane. Methane absorbs red light and reflects blue, which explains the blue-green color. However, a layer of haze particles seems to cover the methane clouds, reducing the amount of light that escapes. This contributes to the planet's darker appearance. Observations from telescopes and spacecraft have shown that Uranus has very few visible cloud features. Compared to Jupiter and Saturn, it looks flat and bland in most wavelengths. This lack of contrast may also reduce the total light reflected. The planet has very low visual activity from Earth's perspective. The Voyager 2 mission, which flew by Uranus in 1986, provided the best close-up images. Even then, the planet appeared mostly featureless and dim. This confirmed that something in the atmosphere is muting its reflectivity. Later models suggest the haze is made of complex hydrocarbons, formed by solar radiation breaking up methane. Newer observations using the Hubble Space Telescope and ground-based telescopes have confirmed that Uranus is consistently darker than expected. Some seasonal changes in brightness have been noted, but the overall reflectivity remains low. These studies continue as better imaging tools become available. Uranus's internal heat is also extremely low. Unlike Jupiter, Saturn, and Neptune, Uranus emits almost no excess heat. This affects atmospheric dynamics, possibly contributing to the planet's static appearance. Less heat means fewer storms, cloud formation, or internal circulation, which keeps the haze in place longer. Seasonal variation on Uranus is affected by its extreme axial tilt. As the planet orbits the Sun, different hemispheres receive sunlight for decades at a time. Despite this, the changes in reflectivity remain minimal. The dark appearance is stable across seasons. Scientists continue to model Uranus's atmosphere to better understand the chemical processes involved. The lack of reflectivity is a key piece in understanding the differences between Uranus and Neptune. Both planets have similar size and composition, but reflect light very differently. In summary, Uranus reflects very little light because of haze layers and low atmospheric activity. Its dim appearance makes it the darkest major planet despite its bright color in telescope images. It's an unusual case among the gas giants, and still not fully explained. Venus spins in the opposite direction of most other planets. Venus has a retrograde rotation, meaning it spins from east to west, opposite to most other planets. It also rotates very slowly. One full spin takes about 243 Earth days. That's longer than a Venusian year, which is about 225 Earth days. Venus rotates so slowly that its day is longer than its year. This backward rotation is unusual in the solar system. Only Venus and Uranus rotate in this direction, and their tilts are very different. For Venus, the tilt is about 177 degrees, meaning it's essentially upside down. Scientists are still unsure what caused this reversal of spin. One leading theory is that Venus may have experienced a massive collision with another body early in its history. The impact could have flipped its rotation or altered its spin direction over time. Another possibility is that gravitational interactions with the Sun and other planets gradually changed its rotation. Tidal forces from the Sun may have also influenced the spin. Because Venus has a dense atmosphere, the Sun's gravity can interact with it more than with planets with thinner atmospheres. Over time, this might have slowed and reversed the rotation. However, this process would take billions of years. Venus's rotation is also very stable, despite being so slow and reversed. Unlike Earth, it doesn't experience significant wobbling or axial precession. This suggests that its current state has existed for a long time. The planet shows no signs of changing its rotation again anytime soon. The retrograde rotation means the Sun rises in the west and sets in the east on Venus. However, due to its slow spin and thick clouds, a full sunrise or sunset would take many Earth weeks. The dense atmosphere also scatters light, so the surface receives diffuse illumination instead of direct sunlight. The rotation affects Venus's weather and cloud patterns. Its atmosphere rotates much faster than the surface, a phenomenon called superrotation. Winds in the upper atmosphere complete a full trip around the planet in just a few Earth days. This creates rapid cloud movement despite the planet's slow rotation. The reversed spin also impacts how we model Venus's interior and core dynamics. The core is believed to be similar to Earth's, but the rotation may change how convection and magnetic fields behave. Venus has no global magnetic field, and some researchers think its rotation is a factor. Future missions to Venus, like Veritas and Da Vinci Plus, may help clarify how and why Venus spins the way it does. These missions will study both surface geology and atmospheric dynamics. Understanding Venus's rotation could provide insights into planetary formation and evolution. Venus's retrograde rotation is one of the most extreme and puzzling features in the solar system. It sets the planet apart in both its day-night cycle and its geological history. Its cause is still debated, but it's a key factor in how Venus behaves today. Mars has seasons like Earth. but they last twice as long. Mars experiences 4 distinct seasons, just like Earth: spring, summer, autumn, and winter. These are caused by the planet's axial tilt, which is about 25 degrees, very close to Earth's 23.5 degrees. This tilt causes sunlight to hit different parts of the planet at different angles throughout its year. As a result, Mars has seasonal variations in temperature and weather. However, a year on Mars lasts about 687 Earth days. That means each season on Mars is roughly twice as long as a season on Earth. For example, Martian summer in the northern hemisphere can last up to 6 months. This extended period affects atmospheric circulation and surface conditions. Mars's orbit is also more elliptical than Earth's, meaning the seasons are uneven in length. Northern summer is longer and milder, while southern summer is shorter and hotter. This happens because Mars is closer to the Sun during southern summer. It causes temperature extremes between hemispheres. During winter, carbon dioxide from the atmosphere freezes and forms polar ice caps. In summer, this CO2 sublimes back into gas, increasing atmospheric pressure. This seasonal cycling contributes to dust storms, cloud formation, and shifting winds. The atmosphere itself expands and contracts with the seasons. Dust storms are more common in southern summer when sunlight is more intense. These storms can grow to planet-wide events, lasting weeks. In some cases, they block sunlight and lower surface temperatures. NASA's Opportunity rover was lost during such a storm in 2018. These storms are driven by seasonal heating differences. Temperatures on Mars can vary greatly with the seasons. In summer, equatorial regions may reach about 20 degrees Celsius during the day, while winter temperatures at the poles can drop below -120 degrees Celsius. The thin atmosphere makes it hard to retain heat. Surface frost and ice can form even near the equator during cold periods. The Martian seasons also affect polar ice caps made of water and CO2 ice. The caps grow and shrink with the seasons, revealing layered deposits. These layers provide a record of Mars's climate history. They are among the best preserved indicators of long-term weather cycles on the planet. Rovers like Curiosity and Perseverance have observed seasonal changes at their landing sites. Changes in air pressure, dust levels, and sunlight vary as the planet moves around the Sun. These changes help scientists understand weather patterns as well as how they impact surface operations and solar panels. Knowing the seasonal cycle is important for planning missions. Solar energy, temperatures, and dust conditions vary significantly. Timing a landing or operation to avoid dust storm season increases success. Seasons also affect potential habitability and the search for water. Mars's long, variable seasons show how similar and different it is from Earth. The planet shares familiar patterns like solstices and equinoxes, but on a longer and more extreme scale. Understanding these cycles helps prepare for long-term exploration and possible human missions. The Moon helps stabilize Earth's tilt, allowing for a relatively stable climate. Earth has an axial tilt of about 23.5 degrees, which causes the changing of seasons. This tilt is stabilized largely due to the gravitational pull of the Moon. Without the Moon, Earth's tilt would vary much more over time. These variations could reach up to 60 degrees, according to some models. That would cause extreme climate swings. The Moon's stabilizing effect comes from tidal forces. As Earth spins, the Moon's gravity pulls on the planet's equator, creating a torque. This helps resist the chaotic influence of the Sun and other planets. It keeps Earth's axial tilt within a narrow range over long time periods. That range has remained stable for millions of years. The tilt directly affects how much sunlight different parts of the Earth receive during the year. If the tilt shifted too much, areas near the poles could become tropical, or equatorial regions could freeze. That would make long-term climate patterns unpredictable, impacting ecosystems and agriculture. Stability is crucial for maintaining life-supporting conditions. Simulations show that without the Moon, Earth's tilt could vary chaotically over time. Mars, for example, has no large moon and experiences unstable axial tilt. Its tilt changes by tens of degrees over geological timescales. The Moon acts like a gravitational anchor, preventing similar chaos on Earth. The Moon also causes ocean tides, but its role in tilt stabilization is independent of that. The stabilizing effect comes from the Moon's mass and orbital distance, not from the tides themselves. A smaller or more distant moon wouldn't provide the same stability. The Moon's size is unusually large compared to Earth. The current configuration of the Earth-Moon system is likely the result of a giant impact early in Earth's history. A Mars-sized object may have collided with Earth, and the debris formed the Moon. This unique event set up the conditions for long-term axial stability. Most planets do not have this advantage. Changes in Earth's tilt do occur, but are minor. They range from 22.1 to 24.5 degrees over a 41,000-year cycle. These are part of the Milankovitch cycles, which influence ice ages and climate shifts. Still, the presence of the Moon prevents far larger and more erratic changes. Jupiter acts like a cosmic shield, deflecting dangerous comets and asteroids. Jupiter is the largest planet in the solar system, and its immense gravity plays a protective role. It can capture, redirect, or eject comets and asteroids that enter the inner solar system. This makes Jupiter a kind of gravitational shield for Earth and the other inner planets. Its position and size are key to this effect. Jupiter's gravity is strong enough to alter the trajectories of many incoming objects. Some are flung into space, while others are pulled into Jupiter itself. There have been several recorded impacts, including Comet Shoemaker-Levy 9 in 1994. That comet broke apart and collided with Jupiter, leaving huge scars in its atmosphere. These collisions show that Jupiter absorbs objects that might otherwise head toward Earth. Its presence reduces the number of potentially hazardous impacts. This doesn't mean it stops all threats, but it helps reduce their frequency. Its role as a cosmic vacuum cleaner is taken seriously in planetary science. Jupiter also affects the asteroid belt between Mars and Jupiter. Its gravity creates orbital resonances that shape the distribution of asteroids. These resonances can destabilize orbits and send fragments toward Earth, but overall, Jupiter keeps the belt from collapsing or forming a planet. It controls the region. In some cases, Jupiter's gravity can deflect comets toward the inner solar system. However, statistical models show that it prevents more impacts than it causes. It changes orbits in complex ways, but the net effect is protective, especially over long timescales. Without Jupiter, Earth would likely experience more impacts. The planet also has many moons, and some of them may contribute to this shielding effect. For example, Ganymede and Callisto could capture or redirect small objects in Jupiter's gravity well. However, the primary shield is Jupiter itself, due to its mass and location. It's the dominant force in the outer solar system. Computer simulations of solar system evolution often include Jupiter's influence. They show that planetary systems without a Jupiter-like planet may be more exposed to debris. Some exoplanet systems lack a gas giant in a similar orbit, which may affect planetary habitability in those systems. Jupiter's orbit is slightly elliptical, but relatively stable. That stability allows it to maintain its gravitational influence over billions of years. If Jupiter had a different orbit, its effect on asteroid and comet paths would be less predictable. Its current position is ideal for its shielding role. Uranus and Neptune are still two of the least understood planets in astronomy. Uranus and Neptune are known as the ice giants of the solar system. Unlike Jupiter and Saturn, which are mostly hydrogen and helium, these planets have more ices, like water, methane, and ammonia in their interiors. Despite their size and importance, they are poorly explored. Only one spacecraft, Voyager 2, has flown past them. Voyager 2 passed Uranus in 1986 and Neptune in 1989, providing the only close-up images we have. Since then, all data has come from telescopes. That means our understanding of their atmospheres, magnetic fields, and internal structure is limited. There are many open questions about their composition and behavior. Uranus has a strange rotation, tilted at about 98 degrees, possibly due to a past collision. Its magnetic field is also highly tilted and off-center. Neptune has a more normal tilt, but an even more dynamic atmosphere, including storms and winds up to 2,000 kilometers per hour, the fastest in the solar system. Both planets have faint ring systems, multiple moons, and complex weather patterns, but their deeper layers remain a mystery. Models suggest they have a slushy, high-pressure mixture of water, ammonia, and methane, but no probe has ever studied these layers directly. Their magnetic fields are irregular and don't align well with their rotational axes. This suggests unusual internal dynamics. On Earth and Jupiter, the magnetic field is created by spinning metallic cores. On Uranus and Neptune, the mechanism might involve ionic oceans or exotic ice phases. New telescopes like James Webb Space Telescope are beginning to provide better data. These tools help study atmospheric composition and temperature patterns. But even with modern instruments, a dedicated mission is needed to fully understand these worlds. Currently, no spacecraft is en route. NASA and other agencies are considering missions like Neptune Orbiter or Uranus Probe. These would explore moons, rings, and internal structure. Such missions are technically challenging due to distance and travel time. It can take over a decade to reach either planet with current technology. Their moons are also of interest. Neptune's Triton may be a captured Kuiper Belt object and is geologically active. Uranus's moons show signs of past activity and may contain subsurface oceans, but without close-up data, these theories remain unconfirmed. Understanding Uranus and Neptune is important for comparative planetology. Many exoplanets discovered so far are similar in size and mass to ice giants. Studying our own ice giants helps scientists interpret data from distant solar systems more accurately. For now, Uranus and Neptune remain largely unexplored. They are the only major planets that have never had a dedicated orbiter. Sending missions to them is one of the highest priorities in planetary science for the coming decades. Temperatures on Mercury range from minus 170 degrees Celsius at night to plus 430 degrees Celsius during the day. Mercury is the closest planet to the Sun, but it has no atmosphere thick enough to trap heat. As a result, its surface experiences extreme temperature swings. During the day, surface temperatures can reach plus 430 degrees Celsius, hot enough to melt some metals. At night, they drop to around minus 170 degrees Celsius, colder than any temperature on Earth. This is one of the widest temperature ranges in the solar system. The lack of atmosphere is the main reason for this variation. Mercury has only a thin exosphere made of atoms blasted off its surface by solar wind and micrometeoroids. It doesn't retain heat like Earth or Venus. Once the sun sets, the heat escapes into space rapidly. The planet's slow rotation makes this effect more extreme. One day on Mercury, from sunrise to sunrise, lasts about 176 Earth days. That means each side of the planet is exposed to long periods of heating or cooling. These extended days and nights contribute to the massive temperature shifts. There's no significant buffer to regulate the surface conditions. During daytime, the sunlight hits Mercury with about 7 times the intensity of what Earth receives. The rocky surface absorbs this energy directly. Without clouds or atmospheric scattering, there's nothing to block or diffuse the sun's rays. The surface heats up quickly, especially near the equator. At night, the lack of insulation means temperatures plunge. Rocks and soil cool down rapidly without an atmosphere to slow heat loss. The coldest regions are often the polar craters, which are permanently shadowed. Some of these areas are cold enough to preserve water ice, despite the planet's proximity to the sun. Spacecraft like Messenger confirmed these extreme temperature conditions. Instruments measured both surface and subsurface temperatures, providing detailed thermal maps. Messenger also found evidence of ice and organic materials in the shaded craters. These discoveries surprised scientists and suggested local thermal stability in some regions. Temperature swings also affect Mercury's geology. The rock expands during the day and contracts at night, creating thermal stress fractures. Over time, this contributes to the planet's unique surface erosion patterns. Cracks in surface breakdown are caused not by wind or water, but by temperature cycling. Mercury's surface is mostly composed of basaltic rock, similar to Earth's volcanic plains. These materials absorb heat efficiently and emit it quickly, which reinforces the extreme thermal response. There's no soil, vegetation, or atmosphere to moderate these changes. Surface composition plays a key role in heat behavior. Thermal variation is a major consideration for space missions. Any lander or rover must survive both intense heat and deep cold. That requires advanced thermal protection systems. As of now, no mission has landed on Mercury, but future missions are being planned with these factors in mind. Mercury's extreme temperatures are a direct result of its lack of atmosphere, slow rotation, and proximity to the sun. The planet serves as a natural laboratory for studying surface-environment interactions in airless worlds. Understanding it helps scientists prepare for missions to other rocky bodies like the Moon or asteroids. Interplanetary dust creates a faint glow in the sky called zodiacal light. Zodiacal light is a dim, diffuse glow visible in the night sky just before dawn or after sunset. It appears along the ecliptic, the path the sun and planets follow. This glow is caused by sunlight reflecting off tiny dust particles in space. These particles form a cloud known as the interplanetary dust cloud. The dust comes from comets and asteroid collisions. As these objects break apart, they release fine particles that spread out along their orbits. The result is a broad, flat cloud of dust that lies mostly in the plane of the solar system. This dust reflects sunlight, creating the faint glow we see from Earth. Zodiacal light is easiest to see in areas with very dark skies and minimal light pollution. It is most visible near the equator during the spring and autumn months. The light looks like a soft, triangular glow rising from the horizon. It's often mistaken for distant twilight, but is unrelated to Earth's atmosphere. The dust particles responsible are very small, often less than a millimeter in size. Despite being small, there are trillions of them, enough to reflect sunlight collectively. The particles are spread thinly but consistently throughout the inner solar system. The densest region lies between Venus and Jupiter. These particles slowly spiral toward the Sun due to Poynting-Robertson drag, a process where solar radiation causes orbital decay. As they move inward, they can be replenished by new dust from active comets or asteroid belts. It's a continuous cycle that maintains the dust cloud over long timescales. Zodiacal dust is also detected by spacecraft. Instruments on probes like Helios, Juno, and Parker Solar Probe have measured this dust directly. These measurements confirmed the structure, composition, and distribution of the dust cloud. The dust plays a role in space navigation and mission planning. The zodiacal light is part of a broader category of sky glow phenomena called sky glow, which includes air glow and Gegenschein. Unlike air glow, which is caused by Earth's atmosphere, zodiacal light is entirely space-based. It is sunlight bouncing off particles floating in space, not related to weather or Earth-based light sources. Some researchers believe that zodiacal dust may interfere with space telescopes. The scattered light can add background noise to astronomical observations. Understanding the dust distribution helps in calibrating instruments and planning observation strategies. It also helps with modeling the infrared background. The origin and behavior of zodiacal dust help scientists understand collisional dynamics in the asteroid belt. Studying this dust also provides clues about solar system evolution, including how debris is generated and transported. It's a small-scale process with large-scale implications. Although faint and easily missed, zodiacal light is a visible result of ongoing processes in the solar system. It connects Earth to the broader cosmic environment. What looks like a soft glow in the sky is actually sunlight bouncing off interplanetary debris that's constantly moving through space. The Sun contains over 99% of all the mass in the solar system. The Sun is by far the most massive object in the solar system. It accounts for approximately 99.86% of the total mass. All the planets, moons, asteroids, and comets combined make up less than 0.2%. The Sun's gravity dominates the system, keeping all planets in orbit. Its mass is the central anchor for everything else. The Sun's mass is about 1.989 times 10 to the 30th kilograms. In comparison, Jupiter, the most massive planet, is only about 0.1% of that. Earth is less than 0.0003% of the Sun's mass. This difference shows how much the Sun controls. It defines the structure, dynamics, and behavior of the entire system. The Sun is composed mostly of hydrogen, about 74%, and helium, about 24%, with trace amounts of heavier elements. It generates energy through nuclear fusion, converting hydrogen into helium in its core. This process releases enormous amounts of energy, which powers the solar wind and emits sunlight. Because of its mass, the Sun creates a deep gravitational well. Any object that moves too close without enough speed will fall into it. This applies to comets, spacecraft, and even light to a small extent. The Sun's mass also shapes the curvature of space-time in its vicinity, according to general relativity. The solar system is structured in layers based on distance and interaction with the Sun. The inner planets are tightly bound due to stronger gravitational influence. Farther out, objects in the Kuiper belt and Oort cloud still feel the Sun's gravity, though much weaker. Even distant comets remain in its domain. The Sun's gravitational force is responsible for planetary orbits, the shapes of asteroid belts, and the paths of comets. Without such a massive central object, the planets would not follow predictable or stable paths. The system would be far more chaotic or completely unstable. The Sun also emits a powerful magnetic field carried through the solar wind. This field shapes the heliosphere, a bubble that extends beyond Pluto. The combination of mass and magnetic activity makes the Sun a multi-layered control system for everything orbiting it. Because of its overwhelming mass, the center of mass of the solar system, barycenter, is often very close to the center of the Sun. However, when large planets like Jupiter and Saturn align, the barycenter can shift outside the surface of the Sun. This causes slight wobbles in its motion. The Sun is expected to keep fusing hydrogen for another 5 billion years. After that, it will become a red giant, then eventually a white dwarf. Even in that state, it will remain the dominant mass in the solar system, although its influence will change. Its mass will remain mostly intact. In any solar system, the star almost always contains the vast majority of mass. In our case, the Sun does more than just provide light, it holds everything together. Its mass is not just a number, it's the reason the planets exist in stable orbits at all. Earth has gone through magnetic field reversals throughout its history. Earth's magnetic field has flipped polarity many times over millions of years. This means the north and south magnetic poles switch places. These events are called geomagnetic reversals. The last major reversal happened about 780,000 years ago, known as the Brunhes-Matuyama reversal. Reversals are detected by studying magnetic patterns in ancient volcanic and sedimentary rocks. The magnetic field is generated by liquid iron moving in Earth's outer core. This movement creates electric currents which produce the magnetic field. Over time, the flow changes, which can lead to weakening, instability, and eventually pole reversal. These changes don't follow a set pattern. The time between reversals can vary from tens of thousands to millions of years. During a reversal, the magnetic field does not vanish, but it becomes weaker and more complex. It may develop multiple poles or shift rapidly before settling into the new orientation. These transitions can take thousands of years. Some periods include temporary reversals or aborted flips, called excursions. Evidence of past reversals is preserved in mid-ocean ridges. As magma solidifies, iron-rich minerals align with the magnetic field. This creates a pattern of magnetic stripes that record the history of pole positions. These patterns are key to understanding plate tectonics and seafloor spreading. Reversals have no known connection to mass extinctions or biological crises. There's no evidence that they cause major harm to life. However, during a reversal, the weakened magnetic field might let more solar and cosmic radiation reach Earth's surface. This could affect satellites, power systems, and atmospheric chemistry. Modern studies track the position of the magnetic North Pole, which is currently moving rapidly toward Siberia. This motion has sped up in recent decades, raising speculation about a future reversal. However, the current behavior doesn't confirm that a flip is near. Changes in pole position are not uncommon. The magnetic field has weakened by about 10% over the last 150 years. This could be part of a natural cycle or a sign of a long-term shift. Scientists continue to monitor it using satellites like SWARM, launched by the European Space Agency. These instruments map field strength and direction globally. A reversal would affect navigation systems that rely on magnetic compasses. Satellites and radio communication could also experience interference. Modern technology is more vulnerable to magnetic variations than previous generations. That's why tracking field behavior is important for infrastructure protection. Animals that use magnetic fields for navigation, such as birds, whales, and turtles, might be temporarily affected. However, many species have survived past reversals. Evolution likely equipped them with ways to adapt or switch to other orientation methods. No mass biological disruptions are linked to reversals. Earth's magnetic field is dynamic and always changing. Reversals are a normal part of its long-term behavior. They reflect the complex fluid motion inside the planet's core. Understanding them improves our knowledge of Earth's interior, atmosphere, and interaction with space. Some of Jupiter's moons, like Europa, have ice crusts with oceans underneath. Europa, one of Jupiter's largest moons, is covered by a thick layer of ice. Beneath this surface, scientists believe there is a liquid water ocean. The ocean may be 100 kilometers deep, far deeper than any on Earth. This makes Europa a key target in the search for extraterrestrial life. Its subsurface ocean is kept warm by tidal heating. Tidal heating happens due to Europa's elliptical orbit around Jupiter. The planet's strong gravity stretches and compresses Europa, creating internal friction. This friction generates heat inside the moon. That heat may prevent the ocean from freezing solid. It also supports the possibility of an active subsurface environment. The ice shell on Europa is estimated to be between 10 and 30 kilometers thick. Cracks and ridges on the surface suggest that the ice moves and shifts. Some regions show evidence of ice tectonics or convection. These processes could help circulate materials between the surface and the ocean. Plumes of water vapor have been detected erupting from Europa's surface. These plumes may come from the subsurface ocean. If confirmed, they offer a way to sample the ocean without drilling. NASA's Europa Clipper mission, launching in the 2020s, will study this possibility in detail. Europa's surface also contains salts and organic molecules, possibly brought up from the ocean. These materials may indicate chemical interactions between water and rock at the ocean floor. On Earth, similar environments near hydrothermal vents support rich ecosystems. Europa might host similar habitats. The Moon has a relatively young surface with few impact craters. This suggests ongoing resurfacing. Tectonic activity or cryovolcanism could be renewing the ice shell. It implies that the interior is geologically active, even though the surface is frozen and airless. The ocean is likely in contact with a rocky sea floor, not just trapped in ice. This is important because interactions between water and rock could produce chemical energy. That energy may support microbial life, even in the absence of sunlight. This makes Europa one of the most promising places for life beyond Earth. Instruments on the Europa Clipper will include radar, spectrometers, and magnetometers. These tools will map the ice shell, detect the ocean, and analyze surface chemistry. Repeated flybys will collect high-resolution data to determine where to search for life in the future. Europa is not the only icy moon with a possible ocean. Ganymede and Callisto may also have subsurface oceans. But Europa is the most accessible and geologically active. It remains the highest priority for astrobiology missions in the outer solar system. Europa's combination of liquid water, heat, and chemistry makes it a natural laboratory for studying life's potential elsewhere. Even though it's cold and distant, the ocean beneath its ice could be more active and complex than it appears. Exploring Europa may answer some of the biggest questions in planetary science. Saturn's rings are made of ice and rock and could disappear in millions of years. Saturn's rings are one of the most iconic features in the solar system. They are composed mostly of ice particles, along with some rocky debris and dust. The particles range in size from tiny grains to chunks several meters wide. Despite their massive appearance, the rings are very thin, usually only about 10 to 100 meters thick. The total mass of the rings is estimated to be only a fraction of a moon's mass. They may have formed from a destroyed moon or comet that came too close to Saturn. The planet's strong gravity tore it apart, creating a debris field. That debris eventually spread into the ring system we see today. The rings are divided into sections labeled A, B, C, and so on. Each ring has gaps and divisions, often shaped by small moons called shepherd moons. These moons influence the particles and keep ring edges sharp. The rings are not solid. They are dynamic systems made of countless orbiting pieces. Saturn's rings are not permanent. Data from the Cassini spacecraft showed that the rings are losing material. Micrometeoroids and solar radiation cause particles to fall into Saturn's atmosphere. This process is known as ring rain. It's gradually depleting the rings over time. Estimates suggest that the rings could disappear in 100 to 300 million years. That may sound distant, but it's short in planetary terms. Some scientists think the rings may be a recent feature, only a few 100 million years old. If so, we live at a rare moment in Saturn's long history. Cassini's final orbits revealed that tons of ring material fall into Saturn every second. These particles are vaporized in the planet's upper atmosphere. The interaction also affects Saturn's magnetic field and ionosphere. It shows that the rings and planet are not isolated systems. Some particles are recycled through collisions and interactions with moons, but this recycling is not enough to stop the long-term loss. The rings may also be affected by Saturn's gravitational field variations, which can disturb the orbits of ring particles. Over time, more material will fall inward. Saturn's rings are highly reflective, making the planet one of the brightest objects in the sky. Their brightness is due to the high ice content. If the rings fade or disappear, Saturn's appearance will change dramatically. Future observers may not recognize the planet as we do now. Other gas giants, Jupiter, Uranus, and Neptune, also have rings, but theirs are much smaller and darker. Saturn's rings are exceptionally large and visible, which makes them an area of intense study. Understanding their origin and fate helps explain disk dynamics throughout the solar system. Saturn's rings are temporary features shaped by collisions, gravity, and time. They are beautiful but fragile, and they will not last forever. Studying them now gives us a chance to understand a short-lived phase in planetary evolution. Radiation from the Sun takes about 8 minutes to reach us. Light and other forms of electromagnetic radiation from the Sun travel at a speed of approximately 299,792 kilometers per second, the speed of light. The average distance from the Sun to Earth is about 150 million kilometers. At this distance, it takes sunlight around 8 minutes and 20 seconds to reach our planet. This means we always see the Sun as it was 8 minutes ago. This delay applies to visible light, ultraviolet rays, infrared radiation, and solar flares. If the Sun suddenly stopped shining, we wouldn't know immediately. We'd only find out 8 minutes later. This time lag affects our real-time understanding of solar events. Solar observatories must account for this delay when monitoring changes on the Sun's surface. The energy we receive on Earth is part of the electromagnetic spectrum, which includes more than just visible light. It also includes ultraviolet radiation, which causes sunburn, and infrared radiation, which delivers heat. All of these components travel at the same speed, the speed of light, so they all take roughly the same time to arrive. This time gap also applies to observations of other planets. For example, light from Mars takes between 4 and 24 minutes to reach Earth, depending on the planet's positions. For spacecraft communications, this delay limits real-time control. Commands sent to distant probes also take minutes or hours to arrive. Neutrinos, subatomic particles produced by nuclear reactions in the Sun's core, also travel nearly at light speed. Unlike photons, they escape the Sun's core instantly and reach Earth before any other form of radiation, but they are hard to detect due to their weak interactions with matter. Although it only takes 8 minutes for sunlight to reach us, the photons themselves take thousands of years to escape the Sun's interior. Inside the Sun, photons are constantly absorbed and re-emitted in a process called radiative diffusion. This delays their exit from the core. Once they reach the surface, they travel quickly through space. Understanding the travel time of solar radiation is crucial for space weather monitoring. Events like solar flares and coronal mass ejections, CMEs, emit both light and energetic particles. While the light arrives in 8 minutes, the charged particles take hours or even days to reach Earth. That gives us some warning of geomagnetic storms. Solar radiation provides nearly all the energy that powers Earth's climate and biological systems. The timing of solar input is factored into climate models, satellite systems, and astronomical calculations. Even small variations in radiation can influence weather patterns and satellite performance. The 8-minute light travel time also has symbolic value in astronomy. It reminds us that we are never seeing anything in real time. Everything we observe is from the past, even within our own solar system. Light has a finite speed, and that sets a limit on how we experience the universe. So every time you see the Sun, you're looking at a snapshot from 8 minutes ago. The delay is constant, predictable, and built into nearly every calculation involving the Sun and Earth. It's a small but measurable separation between us and our main energy source. The core of the Sun is hotter than anything else in the solar system. The Sun's core is the hottest known region in the solar system, with temperatures reaching around 15 million degrees Celsius. This intense heat is produced by nuclear fusion, the process that powers the Sun. In the core, hydrogen atoms are fused into helium, releasing massive amounts of energy. This process only happens at extreme pressure and temperature. The fusion reaction in the core is known as the proton-proton chain reaction. It converts mass into energy according to Einstein's equation E equals mc squared. Every second, the Sun converts about 600 million tons of hydrogen into helium, releasing vast amounts of light and heat. Most of this energy eventually reaches Earth as sunlight. The core is located in the innermost 25% of the Sun's radius. Above it lies the radiative zone and then the convective zone. Energy produced in the core takes thousands to millions of years to reach the surface. After escaping the surface, it takes just 8 minutes to reach Earth. Nowhere else in the solar system comes close to the Sun's core temperature. The surface of the Sun, the photosphere, is much cooler, around 5,500 degrees Celsius. Venus, the hottest planet's surface, reaches only about 470 degrees Celsius, and even Jupiter's core is estimated to be less than 30,000 degrees Celsius. Nothing naturally occurring in the solar system rivals the Sun's core. This extreme heat is balanced by enormous pressure. The Sun's own gravity compresses its inner layers, creating the necessary environment for fusion. Without enough mass, a star wouldn't ignite fusion and would remain a brown dwarf. The Sun is just massive enough to sustain stable fusion for billions of years. The heat and pressure at the core are so high that atoms lose their electrons, forming a plasma, a state of matter where nuclei and electrons are free. This plasma is highly conductive and plays a key role in generating the Sun's magnetic field. The behavior of plasma under such extreme conditions is still a subject of research. Scientific models of the core are tested using helioseismology, which studies sound waves moving through the Sun. These waves give indirect information about density, temperature, and composition inside the Sun. Since we can't see the core directly, this method helps confirm our understanding. Fusion in the Sun's core produces neutrinos, which escape instantly and reach Earth in minutes. These particles are detected by specialized instruments like Super Kamiokande in Japan. Measuring them helps confirm that fusion is happening as predicted. They are one of the only direct signs of core activity. Artificial fusion reactors on Earth attempt to replicate this process, but at much lower scales. So far, no human-made device has matched the sustained energy output or efficiency of the Sun's fusion. Studying the Sun helps scientists design better fusion experiments on Earth. The Sun's core is the power source of the entire solar system. Its heat drives planetary climates, enables life on Earth, and defines the energy balance of the solar environment. It remains the most extreme and energy-rich place we've ever studied. There is a giant plasma bubble around the solar system called the heliopause. The heliopause marks the outer boundary of the heliosphere, the region where the Sun's solar wind dominates. Beyond the heliopause lies interstellar space, where particles and radiation come from other stars. It's the point where the pressure from the solar wind is balanced by that of the interstellar medium. This boundary forms a giant plasma bubble around our entire solar system. Inside the heliosphere, the solar wind flows outward in all directions. As it travels farther from the Sun, it slows down and eventually reaches the termination shock. This is where the solar wind drops below supersonic speeds. Between the termination shock and the heliopause is the heliosheath, a turbulent region of slowed, compressed plasma. The heliopause was crossed by Voyager 1 in 2012 and Voyager 2 in 2018. These spacecraft provided direct data about conditions at the edge of the Sun's influence. They detected changes in particle density, magnetic fields, and radiation levels. This confirmed that they had left the heliosphere and entered interstellar space. The shape of the heliosphere and heliopause is not perfectly round. It's distorted by the Sun's motion through the galaxy and the uneven flow of interstellar material. Models suggest a comet-like shape with a blunt front and a trailing tail. New data from probes like IBEX and Voyager help refine our understanding of its structure. The heliopause plays a major role in shielding the solar system from galactic cosmic rays. These high-energy particles can be harmful to spacecraft electronics and biological systems. Inside the heliosphere, the Sun's magnetic field and solar wind deflect many of them. Beyond the heliopause, cosmic ray intensity is much higher. The heliopause is estimated to be about 120 to 150 astronomical units, AU, from the Sun. That's roughly 18 to 22 billion kilometers. These distances vary depending on solar activity and interstellar conditions. During solar maximum, the heliosphere expands. During solar minimum, it contracts slightly. This boundary is dynamic. It moves depending on changes in solar wind speed, density, and interstellar pressure. The heliopause is not a fixed wall, but a flexible zone where two plasma environments interact. It marks the outermost layer of the Sun's influence. Studying the heliopause helps scientists understand stellar environments and how stars interact with the interstellar medium. It also informs our models of how cosmic rays propagate and how other stars might shape their surrounding space. The Sun is not unique. All stars with solar wind have astrospheres. Future missions, such as Interstellar Probe, aim to study the heliopause in greater detail. These probes would go farther than Voyager, measuring magnetic fields, dust, and radiation in the interstellar medium. This would provide clearer data on the transition zone between star systems. The heliopause is the invisible edge of the solar system's domain. It defines where the Sun's influence ends and the galaxy begins. It's a key boundary in space science, not a barrier, but a changing line between solar and interstellar environments. The solar cycle influences Earth's climate in ways still not fully understood. The solar cycle is an 11-year pattern of activity that affects the number of sunspots, solar flares, and solar radiation. During solar maximum, the Sun has more sunspots and emits more ultraviolet and X-ray radiation. During solar minimum, it's calmer and has fewer active regions. These changes affect Earth's upper atmosphere and magnetic environment. Solar activity influences space weather, which can affect satellites, GPS, and power grids. But its link to Earth's long-term climate is more complex. Some studies suggest solar cycles may slightly influence global temperatures, but the effect is small compared to greenhouse gases. Still, understanding the connection is important for climate modeling. Sunspots are darker, cooler regions caused by intense magnetic fields. Paradoxically, more sunspots mean higher total solar output because the surrounding regions are brighter. This increase in energy can heat Earth's upper atmosphere. The effect on surface temperatures is measurable but subtle. Solar flares and coronal mass ejections, or CMEs, are more common during solar maximum. These events don't cause weather directly, but they can change the structure of the ionosphere, which in turn affects radio communications and satellite orbits. In some cases, they even trigger auroras at lower latitudes. Ultraviolet radiation from the Sun varies significantly over the solar cycle. UV radiation affects the ozone layer and upper atmosphere chemistry. Some scientists believe these changes can influence jet streams and weather patterns, though the mechanisms are still under study. The full impact on climate systems remains unclear. Tree rings, ice cores, and historical records show that solar cycles have existed for centuries. Periods of low solar activity, like the Maunder minimum, 1645 to 1715, coincided with cooler temperatures on Earth, known as the Little Ice Age. This suggests a possible connection between prolonged low activity and regional climate cooling. However, modern climate change is mainly driven by human-caused greenhouse gas emissions. Solar cycles contribute only a small fraction to current warming trends. Still, solar variability adds natural fluctuations to climate data, which researchers must account for in their models. It's part of the overall climate system. NASA and other agencies monitor the solar cycle using satellites like SOHO and SDO. These missions track sunspot numbers, solar radiation, and magnetic field changes. By observing the Sun continuously, scientists improve predictions of solar storms and long-term trends. This helps protect both technology and infrastructure. The current solar cycle began in 2019 and is expected to peak around 2025. Each cycle varies in intensity, and researchers watch for unexpected shifts that might signal new patterns. Some scientists also explore longer cycles that span hundreds of years, which might influence broader climate behavior. While the Sun clearly affects Earth's atmosphere, the climate response is complex. More research is needed to understand how solar variations interact with oceans, clouds, and atmospheric circulation. The solar cycle is just one piece of a much larger climate puzzle. Meteorites that fall to Earth carry traces of the solar system's origin. Meteorites are pieces of rock or metal that survive their fall through Earth's atmosphere and land on the surface. Most come from the asteroid belt, and a few originate from the Moon or Mars. These space rocks are important because they often contain material unchanged for billions of years. They are like time capsules from the early solar system. Some meteorites are older than any rocks on Earth. Their chemical makeup reveals conditions from over 4.5 billion years ago, when the Sun and planets were forming. These meteorites often contain chondrules, round particles formed by rapid melting and cooling. Chondrites are among the most primitive materials known. By studying isotopes in meteorites, scientists can learn about radioactive decay, solar wind exposure, and early planet formation. Certain isotopes, like aluminum-26, help date the time of solidification. This provides clues about how quickly the solar system formed and how material moved through space. Some meteorites contain organic molecules, including amino acids. These are not life, but they are the building blocks of life. Their presence suggests that prebiotic chemistry was active in space even before Earth formed. This supports the idea that ingredients for life may have been delivered from space. Iron meteorites come from the cores of broken-up planetary bodies. Their structure shows how metal separates from rock during planetary formation. These samples help scientists understand the internal structure of planets and moons, including Earth. They give direct evidence of differentiation, the process where planets form layers. A small number of meteorites have been identified as coming from Mars. These rocks were blasted into space by impacts and eventually landed on Earth. Their gases match the Martian atmosphere. Studying them provides insights into Martian geology and possible past water activity, long before any rover got there. Meteorites are classified into three main types: stony, chondrites and achondrites, iron, and stony iron. Each type offers different information about planetary formation, asteroid collisions, and space chemistry. Museums and labs around the world keep large collections for research. Antarctica is one of the best places to find meteorites. Dark rocks are easy to spot against the ice, and the cold preserves them well. Thousands of meteorites have been recovered from the region, helping build a more complete picture of the solar system's early history and structure. Meteorite impacts also play a role in shaping Earth. The Chicxulub impact, which contributed to the dinosaur extinction, shows the destructive potential of large meteorites. Studying ancient impacts helps us understand the risks of future collisions and planetary defense. In summary, meteorites are physical records of solar system formation, planetary evolution, and cosmic chemistry. Every specimen adds to our understanding of where we came from and how the materials that make up our planet were formed in space long before Earth existed. Gas giant planets have rocky cores surrounded by dense layers of gas. Jupiter, Saturn, Uranus, and Neptune are called gas giants, or ice giants for Uranus and Neptune. Despite their massive gaseous atmospheres, these planets are believed to have solid or rocky cores at their centers. The cores formed early, attracting large amounts of gas from the protoplanetary disk. This process created planets with thick outer layers and dense centers. The cores of gas giants are composed of rock, metal, and ices, depending on the planet. Jupiter and Saturn likely have solid cores that are 5 to 15 times the mass of Earth. These cores are surrounded by metallic hydrogen, a phase of hydrogen that acts like a metal under extreme pressure. This layer conducts electricity and contributes to planetary magnetic fields. Uranus and Neptune have smaller gaseous envelopes and larger cores rich in water, ammonia, and methane ices. That's why they're often called ice giants instead of gas giants. Their interiors are less dominated by hydrogen and helium and more by volatile materials. These cores still contain rock and metal as well. The exact composition of the cores is not directly observable. Instead, scientists use gravity measurements, magnetic fields, and seismology models to estimate the internal structure. Space missions like Juno at Jupiter and Cassini at Saturn provide detailed data on gravity and motion. These help infer what lies beneath the clouds. Jupiter's strong magnetic field and powerful gravity hint at a dense, heavy core. But recent data suggest it may be partially dissolved or fuzzy rather than clearly defined. That means the core materials could be blended with surrounding layers, not forming a sharp boundary. This idea is still being tested. Saturn likely has a more defined core, but it may also be mixed with layers of ice and hydrogen. Differences in rotation speed and magnetic field shape provide clues to its interior. Uranus and Neptune remain poorly explored, but models suggest they have rocky cores covered by icy mantles and gas. All gas and ice giants formed beyond the frost line in the early solar system. That's the region where temperatures were low enough for ices to condense. This allowed their cores to grow large enough to capture thick atmospheres before the gas in the solar nebula was lost. Terrestrial planets couldn't do this. Understanding gas giants' interiors helps explain how planetary systems evolve. Their gravitational influence shaped the orbits of other planets and small bodies. Studying them also helps in analyzing exoplanets, many of which are gas giants found around other stars. Future missions, especially to Uranus and Neptune, aim to improve our understanding of core composition. Better data on mass distribution, magnetic fields, and atmospheric behavior will help scientists refine interior models. These planets hold important clues about how planets grow and evolve. In short, gas giants are not just made of gas. They are structured worlds with dense, rocky, or icy cores, hidden beneath thick layers of hydrogen, helium, and other elements. Their internal makeup is key to understanding planet formation and the architecture of our solar system. Natural satellites can turn into rings if they get too close to their planets. Moons that orbit too close to a planet can be destroyed by tidal forces. These forces are caused by the planet's gravity pulling more strongly on the side of the moon that is closer. If the moon crosses the Roche limit, the gravitational pull can tear it apart. The debris can then form a ring system around the planet. The Roche limit depends on the planet's size, mass, and the density of the satellite. If a moon moves inside this critical distance, it can no longer hold itself together by its own gravity. It will break apart and the fragments will spread into orbit, creating rings. This is one possible way ring systems form. Saturn's rings may have originated this way. Some scientists believe a former moon came too close and was destroyed. The material stayed trapped in orbit, eventually forming the wide ring system we see today. Other planets like Uranus and Neptune might also have rings formed from broken moons. Jupiter's rings are faint and made mostly of dust, likely from small moons struck by micrometeoroids. These impacts knock debris into orbit, forming thin rings. But in cases where a larger moon is pulled apart, the resulting rings can be much thicker and brighter, like Saturn's. The process of moon destruction is not instant. As the moon spirals inward, it gradually becomes more distorted by tidal stretching. Eventually, it starts to lose material and the debris spreads along its orbit. This gradual destruction can lead to temporary arcs before a full ring forms. Artificial satellites around Earth are safe from this because they are well outside the Roche limit. The process only affects large natural moons with orbits that decay over time or were disturbed. Tidal forces are extremely powerful near massive gas giants, where most large ring systems are found. The reverse is also possible. Ring particles can clump together and form new moons outside the Roche limit. This process is called accretion. In some models of Saturn's history, moons may have formed, then destroyed, and reformed multiple times. It's part of the dynamic life cycle of planetary rings. Computer simulations help researchers test how different moons would behave near their planets. These models show how long it would take for a moon to break apart and what kind of ring system would result. Factors like composition, size, and orbital speed all influence the outcome. The best-known example of a potential future moon destruction is Mars's moon Phobos. It's slowly spiraling inward and may cross the Roche limit in tens of millions of years. If that happens, Mars could temporarily gain a ring made of Phobos debris. So, under the right conditions, a moon can become a ring system, given enough time and the right distance. This process helps explain how some of the most beautiful features in the solar system might have started from violent gravitational forces acting on ancient satellites. The moon had active volcanoes billions of years ago. The moon was volcanically active in its early history. Evidence shows that volcanic eruptions occurred between 4 and 1 billion years ago. These eruptions released lava that filled large impact basins, creating the dark regions we see today, known as lunar maria. The smooth, flat appearance of these areas confirms past volcanic activity. The lunar maria are mostly found on the near side of the moon. They cover about 16% of the lunar surface and are rich in basalt, a type of volcanic rock. These regions formed when magma rose from the moon's interior through cracks in the crust. The lava spread and cooled, forming large, dark plains. Unlike Earth, the moon doesn't have plate tectonics. Its volcanic activity was mostly driven by internal heat left over from formation and by radioactive decay. Over time, the moon cooled and solidified, ending most volcanic processes. By around 1 billion years ago, most eruptions had stopped. Some areas may have experienced small eruptions as recently as 100 million years ago, based on new data from lunar orbiters. These younger flows are rare and limited in size, but they suggest the moon's interior may have remained warm longer than expected. However, these were not major eruptions. Volcanic features on the moon include lava plains, rills, domes, and collapsed tubes. Rills are long, narrow valleys formed by flowing lava. Domes are raised areas where lava bulged but didn't break the surface completely. These features are key clues to past volcanic behavior. Samples from the Apollo missions include volcanic rocks. These help determine the ages and compositions of past eruptions. The lunar basalts are similar in chemistry to those on Earth, but lack water. Their structure confirms that the moon had internal heat and magma systems early on. The moon's volcanic history is important for understanding planetary cooling and evolution. Its early eruptions released gases like argon and helium, forming a temporary thin atmosphere. However, the moon's gravity was too weak to keep these gases, and they escaped into space. New lunar missions aim to study volcanic areas in more detail. China's Chang'e 5 missions have brought back younger basalt samples that fill in gaps left by Apollo. Future missions plan to analyze volcanic domes and lava tubes, which may even be sites for future lunar bases. Unlike Earth's explosive volcanoes, the moon's eruptions were likely gentler and more fluid, forming broad plains rather than mountains. That's because lunar magma had lower gas content. The moon lacks the plate boundaries and tectonic compression that fuel explosive volcanism on Earth. The Moon is no longer volcanically active today, but its surface preserves a detailed record of its geologic past. By studying its volcanic history, scientists gain insights into how rocky planets cool, evolve, and lose their internal heat over time. Pluto has seasonal atmospheres that appear and vanish with its orbit. Pluto's orbit is highly elliptical, which means its distance from the Sun changes significantly over time. When it gets closer to the Sun, its surface ices warm and sublimate, turning directly into gas. This process creates a temporary atmosphere, mostly made of nitrogen, with some methane and carbon monoxide. As Pluto moves farther from the Sun, temperatures drop. The gases in the atmosphere refreeze and settle back onto the surface as frost. This cycle of freezing and sublimation creates seasonal changes in atmospheric pressure and thickness. The atmosphere can nearly vanish at Pluto's farthest point. Pluto takes about 248 Earth years to complete one orbit. Its seasons last for decades, not months like on Earth. Because of this, Pluto's atmosphere behaves differently from any planet. It exists only part of the time, depending on Pluto's position in orbit and surface temperature. Observations from Earth and from the New Horizons mission confirmed this behavior. When New Horizons flew by Pluto in 2015, it detected a thin but stable atmosphere, even though Pluto was already moving away from the Sun. This surprised scientists who expected the atmosphere to already be collapsing. The atmospheric pressure on Pluto is extremely low, less than 100,000th of Earth's pressure at sea level. Despite this, the atmosphere creates haze layers that stretch over 200 kilometers above the surface. These hazes are made of tiny particles formed from solar radiation breaking down methane. Pluto's surface has large ice sheets, mountains, and glaciers made mostly of nitrogen and methane ices. When these ices warm, they fuel the atmospheric cycles. Some regions expand and contract as gases shift. This behavior is similar to seasonal frost cycles on Mars, but even more extreme. The atmosphere may also cause slow winds and shifting haze layers. Although thin, the atmosphere likely helps transport heat around Pluto's surface. It plays a role in reshaping some landscape features. However, these effects are subtle due to the low pressure and temperature. Pluto's tilt, about 120 degrees, also affects how sunlight hits the surface. This tilt leads to long periods of sunlight or darkness at each pole, similar to Uranus. These extreme seasonal patterns add to the changes in surface temperature and gas activity. Scientists continue to observe Pluto using telescopes on Earth, tracking how the atmosphere evolves. They measure how much starlight Pluto blocks during occultations, when it passes in front of a star. These events reveal how thick or thin the atmosphere is at different times. Pluto's temporary atmosphere is unique in the solar system. No other known object forms and loses an atmosphere in quite the same way. It highlights how distance, sunlight, and surface ice can work together to create dynamic behavior on even the most distant worlds. Sun-grazing comets crash into the Sun and vaporize almost instantly. Some comets, called sun-grazers, follow orbits that take them extremely close to the Sun. These objects often belong to the Croits family, a group of comets thought to be fragments of a larger one that broke apart centuries ago. As they approach the Sun, they are subjected to extreme heat and tidal forces. Most don't survive the journey. Many crash directly into the Sun and evaporate in moments. Sun-grazers can heat up to thousands of degrees Celsius near the sun's surface. Their ices and volatile compounds rapidly turn into gas and plasma, creating bright tails before disintegration. The radiation and gravity are so intense that even large comets can't hold together. Some disintegrate before impact, others plunge in fully and are destroyed. Space-based solar observatories like SOHO and STEREO have captured hundreds of these events. They help track sun-grazers as they approach the sun and often catch them vanishing in real time. These instruments have dramatically increased the number of known sun-grazing comets. SOHO alone has discovered over 4,000. Most sun-grazers are very small, often only a few meters across, which is why they are not visible from Earth. But their sudden appearance and destruction provide valuable data on solar behavior and comet composition. When observed closely, they can also help map the structure of the sun's outer layers. Larger sun-grazers are rare but more impressive. One example is Comet Lovejoy, C/2011 W3, which survived a close solar pass but eventually broke apart. Its survival stunned scientists, as it got within 140,000 kilometers of the sun's surface, well inside the solar corona. The main forces acting on these comets are thermal stress, tidal stretching, and solar radiation pressure. The closer they get, the stronger these forces become. Even if a comet is held together by solid rock, the gravitational gradient across its body can rip it apart. Some sun-grazers break into smaller fragments just before impact. These fragments may follow slightly different paths, but most still end up vaporizing. Occasionally, a fragment might survive a single pass and be observed again on a future orbit, though this is rare. These events contribute dust and ionized gas to the sun's corona. Though tiny compared to the mass of the sun, they can help researchers understand how material interacts with solar magnetic fields. They also test our ability to model high-energy solar environments. The study of sun-grazing comets has practical value. It gives insight into how small bodies behave under intense radiation and gravity, useful for understanding how materials might behave near other stars. It also shows how dynamic and active the space near the sun can be. In short, sun-grazers are comets that get too close to the sun and are destroyed, either by evaporation, fragmentation, or collision. These events are brief but scientifically valuable, offering a rare look at extreme conditions in the inner solar system. Jupiter's equator spins faster than its poles, a phenomenon called differential rotation. Jupiter is not a solid planet. It's made mostly of gas and liquid, which allows different parts of the planet to rotate at different speeds. This is called differential rotation. At Jupiter's equator, the atmosphere completes a rotation about 5 minutes faster than at the poles. It's one of the most extreme examples of this in the solar system. Jupiter's equatorial regions rotate roughly every 9 hours and 50 minutes, while the poles take closer to 9 hours and 55 minutes. Because the planet is fluid, there's no single surface to track. Scientists must define rotation rates based on magnetic fields, atmospheric features, or internal motions. The differential rotation drives the formation of Jupiter's bands, zones, and storms. It creates massive jet streams that circle the planet in alternating directions. These winds reach speeds of up to 400 kilometers per hour and give Jupiter its striped appearance. One of the results of this rotation is the Great Red Spot, a massive storm that has lasted for centuries. The storm is powered by the shear between different rotating layers. Without differential rotation, features like this might not exist or would behave differently. Jupiter's rapid rotation, the fastest of any planet, also causes it to bulge at the equator. The planet is an oblate spheroid, flattened at the poles and wider at the equator. This shape amplifies the difference in rotational speed and affects the distribution of mass and gravity. Observations from missions like Voyager, Galileo, and Juno have helped map how rotation varies by latitude and depth. Juno's measurements of gravity and magnetism suggest that the differential rotation extends deep below the cloud tops, possibly several thousand kilometers. The behavior is not unique to Jupiter. Saturn, Uranus, and Neptune also show differential rotation, though not as strongly as Jupiter. Even the Sun exhibits this, with its equator rotating faster than the poles. It's a common feature in fluid or plasma-rich bodies. Differential rotation is caused by the conservation of angular momentum in a non-rigid medium. In Jupiter's case, internal convection and external forces help maintain different speeds. These dynamics are still being studied, as they also relate to heat transport and magnetic field generation. Models of gas giants must account for this rotation to predict weather systems, internal structure, and energy flow. Differential rotation is one of the most important factors in understanding gas giant behavior. It creates a planet that is constantly changing and moving at many layers. In summary, Jupiter spins so fast and is so fluid that its equator rotates faster than its poles. This phenomenon, differential rotation, shapes the planet's weather, structure, and appearance, and it's key to understanding how giant planets behave. Earth sometimes captures tiny temporary moons that orbit for short periods. Earth doesn't just have one moon. Occasionally, it captures small asteroids or rocks that enter our planet's gravity well and temporarily become satellites. These objects are called temporarily captured orbiters, or mini-moons. They typically stay in orbit for a few months to a few years before escaping or falling to Earth. These bodies are very small, usually just 1 to 10 meters in diameter. Because of their size and irregular orbits, they are hard to detect. One confirmed example is 2006 RH-120, a mini-moon that orbited Earth for about 11 months before leaving in 2007. Others have likely passed undetected. Mini-moons enter Earth's orbit when their path through space brings them just close enough to be slowed by gravity. Their orbits are often unstable and chaotic, meaning they can easily be ejected or pulled in by the Moon or Earth itself. Some burn up as meteors, others return to solar orbit. These temporary satellites are different from artificial satellites, which are placed in predictable orbits. Mini-moons have irregular, inclined paths and are usually discovered only after being caught. Their orbits often cross between Earth and the Moon, making tracking even harder. Scientists are interested in mini-moons because they offer a chance to study small asteroids up close. Since they stay near Earth, they could be targeted for exploration or sample return missions. Capturing and analyzing one would help understand the composition of primitive solar system material. Some ideas suggest these objects could be used as test beds for mining or planetary defense techniques. Their small size and close proximity make them safer for practice. However, capturing one intentionally would require precise tracking and timing. Models suggest that Earth may have at least one mini-moon at any given time, although most are too faint to detect. Improved sky surveys and telescope networks may help spot more of them in the future. Each detection helps build better models of how these objects behave. Mini-moons may also contribute to the population of fireballs and meteorites. If one enters Earth's atmosphere, it can burn up and create a bright light. Occasionally, fragments survive and land as meteorites, offering physical samples of the early solar system. These tiny moons help us learn more about near-Earth objects and how planets interact with small bodies. They are short-lived, but their orbits show the complex gravitational dance between Earth, the Moon, and the Sun. Even small rocks can follow fascinating and unpredictable paths. Even without an atmosphere, Mercury has auroras caused by solar particles. Mercury does not have a thick atmosphere like Earth, but it still shows aurora-like activity. This is possible because Mercury has a magnetic field, which can interact with charged particles from the Sun. These interactions cause energetic events on the surface, especially near the magnetic poles. While not true auroras like Earth, the process is similar in principle. On Earth, auroras happen when solar wind particles collide with atmospheric gases, creating glowing lights. Mercury's atmosphere is too thin for that. It has a very weak exosphere, not dense enough to produce visible auroras. Instead, the charged particles hit the surface directly, releasing energy in the form of X-rays and ultraviolet light. Mercury's magnetic field is about 100 times weaker than Earth's, but it's still strong enough to create magnetospheric boundaries. These guide solar wind particles toward the surface, especially near the poles. The result is a type of precipitation of particles, which can be detected by scientific instruments. The Messenger spacecraft, which orbited Mercury between 2011 and 2015, made several discoveries about these interactions. It found evidence of flux transfer events, short bursts of solar particles entering Mercury's magnetic field. These events caused local changes in surface radiation and particle levels. When solar particles strike Mercury's surface, they cause the emission of X-rays, which bounce off and can be observed from orbit. These emissions are often concentrated near magnetic poles, similar to how auroras concentrate near Earth's poles. However, they are not visible to the naked eye. They are detected with sensors. Unlike Earth, Mercury doesn't have a thick atmosphere to protect it from the solar wind. That means solar particles reach the surface more directly and frequently. This constant bombardment alters the surface chemistry and may even help produce its thin exosphere, as atoms are knocked off the ground. Mercury's exosphere contains elements like sodium, potassium, and calcium, which can glow faintly in ultraviolet light. These atoms may be released during particle impact or thermal processes. While this doesn't form a glowing sky like Earth's, it's another form of solar interaction with surface material. The pattern of these emissions can change with solar activity. During solar storms or coronal mass ejections, the flow of charged particles increases. This boosts the number of impacts on Mercury's surface, leading to stronger X-ray and UV emissions, especially in polar and equatorial regions. Mercury's aurora-like activity provides clues about space weather on rocky planets. It also helps scientists understand how magnetic fields protect planetary surfaces and what happens when that protection is weak. It's an extreme example of how a magnetic field alone, even without a real atmosphere, can shape surface behavior. In summary, Mercury has no visible auroras, but it does experience aurora-like particle impacts driven by its magnetic field and solar wind interactions. These events produce energetic emissions and contribute to the planet's dynamic surface environment despite the lack of a thick sky.